optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems.
Attention all the guests, the photographer on our stage will be taking a group of photos for us. Please look forward to the camera on the stage. 1, 2, 3, cheers! Thank you.
Dear professors and distinguished guests, welcome to the 2026 Kopernik Forum. I'm Dr. Meilin Wang from the Huawei Theory Lab and the Kopernik Research Center of Huawei. The Kopernik Research Center is located in Warsaw, and the Kopernik Forum is jointly organized by Park and the Huawei Theory Lab and the Huawei Kopernik Research Center. And we are aimed at to gather the talent mathematical researchers and interdisciplinary researchers to spark new ideas. And this year we are honored to welcome great researchers from 8 countries to here. And we are also honored to welcome Director Jiang Rui from Kopernik Research Center. Now welcome to Director Jiang Rui to give out the welcoming address.
Good morning, ladies and gentlemen. Scholars from all over the world. It's my great pleasure to be here to welcome all of you to our second Kopernik Forum in Shenzhen. As we know, the Kopernik Forum is held by the Park and the Theory Research Lab and our research center. And last year, we held the first forum in our office in Warsaw, in Poland. And we invited 6 outstanding professors and PhDs from Europe. And I think it's a wonderful beginning of our journey. And this year, we are glad to welcome the scholars from across the world to be here in Shenzhen. And I think it's, this is a great thing because I think the forum has grown wider and more international, just like the spirit of Kopernik, to question, to explore, and to seek truth. I'm a little generous, exciting. As we all know, I think the mathematics is the lays a solid foundation for the artificial intelligence, and the AI brings new directions to the mathematics research. So this combination of these two brings the continuous science innovation. So here, I hope all of us can exchange our ideas freely and share our research and inspire each other. And maybe we can build the long-term operation in academia. So finally, let me welcome you again. And I wish this forum a great success. Thank you.
Thank you for Mr. Jiang Rui's warm remark. And today for this conference, we have 6 sessions throughout the conference, and with 2 sessions every half day. And a group photo will be taken during this afternoon's coffee break. Okay, let's move on to the official agenda. The chair of the first session is Professor Jinqiao Duan. Professor Duan was Associate Director of the Institute for Pure and Applied Mathematics of USA. Now he is the Chair Professor in Mathematics and in Physics, Great Bay University, China. Also the Executive Dean of School of Sciences in Great Bay University. He works in stochastic dynamical systems and stochastic partial differential equations, machine learning, and stochastic dynamics with applications in biophysical and geophysical systems. His books include An Introduction to Stochastic Dynamics and the Effective Dynamics of Stochastic Partial Differential Equations. Welcome, Jin Chaoduan.
Good morning, everyone. Good morning, distinguished guests and the friends and the colleagues from around the world, and especially for our students and the researchers online at Kopernik Forum. So the first presentation is going to be by Dr. Sergei Nikolenko from Russia. And Sergei is with Stakhanov Mathematical Institute of Russian Academy of Sciences, and he's also with St. Petersburg State University. He's a research and a professor in machine learning, data science, AI, especially AI and mathematics. He is a recipient of the Index Machine Learning Prize in 2023 in Russia. And he has taught many online and offline courses in machine learning, AI, especially AI and mathematics. Today, Sergei is going to share with us AI in mathematics, history, state of the art, and the future, especially the near future. Let's welcome Sergei.
All right, thank you very much. I quite often give this talk about how AI progresses in math. I do it about twice a year, and every time some completely new results show up. And since I'm giving it very often, I have about 100 slides for you. And only 30 minutes, maybe 35 now that the introduction took a little bit less time. But still, I'm going to be skipping a lot. Don't worry. It's just a popular talk about, how AI can help us in math and where we mathematicians fall in that, and how this all works right now and what to expect. So let's dive in. My first part is going to be very brief because I'm sure everyone here understands completely all of the current status and implications. But, AI is progressing really, really quickly. That's the whole point of my first part. So this is an AI timeline, how it would look, 10 years ago. That's one of the images that I usually start my 2-year-long course on machine learning with. So like a regular science, right? And then, this is another timeline of AI or deep learning as a regular science. But lately, in the last few years, AI timelines look more like this, right? They look like, I made this picture in the middle of 2023, after the revolution of LLMs, after ChatGPT appeared and everything. And at first I thought it would be a picture about, the spring of AI, as I called it back then. And I thought it would be an explosion, like it always happens in different areas of science, and then they like gas, the science fills in the new space, and then pressure equalizes, and then you wait for the new breakthrough, right? Well, so far it didn't happen. It keeps accelerating, right? And this is the timeline of the race for O1 replication in 2020, in early 25. But I could do a picture like this for every month in the last 3 years, and it would be just as impressive for every month. So what does it mean? What does it mean? Of course, the big questions are, what does it mean for humanity? How are we going to deal with the coming AGI, which some argue is already with us. Some argue will be here in 2 years. Some pessimists argue it will be with us in 5 years. So anyway, we are going to live to see it. Will it lead to the technological singularity? kind of obviously, almost obviously, yes, but what does it actually mean? Nobody knows. And these are, of course, questions without answers, but today I am discussing a much more narrow topic, right? So what does it mean for mathematics? How does AI reflect back on mathematics that created it? And where are mathematicians in that, right? And what do I think is going to happen with mathematics and AI in the near future? Okay, so let me step back now, back to that original timeline that I like to show. Let's step back to the history of AI in mathematics, and the first, like the idea that I want to that I want to put through in this part is that AI in mathematics so far, until maybe the last year or so, has been surprisingly unproductive. Surprisingly so, right? Because, and it has always puzzled me, right? I actually, at some point, I specialized in, and I did some work in mathematical logic, so I know that field. And since Hilbert, since Frege, since Gödel and Gentzen and all of these nice people, we've kind of known how to formalize mathematics, right? Since Robinson's resolution, we've kind of known how to build automated theorem provers. And we could never prove anything automatically. It just didn't work. It never, ever worked. And of course, if you know any mathematical logic, you would tell me that but it's not supposed to work, right? It's hopelessly difficult in the worst case. There are unprobability theorems. There are statements that take a universe to prove, etc., etc. Well, sure, in the worst case, but we do not live in the worst case, right? Sure, there will always be unprovable statements and statements that are provable but too hard for us. Sure, absolutely. But my point is, over these 50 years of automated theorem proving, we have not been able to prove anything at all. Not just, not everything, but not anything. This has always been a mystery to me. It still is. Maybe so. Maybe one of you can answer why this is so. And actually, AI as a science, AI as a practical and research endeavor started with automated theorem proving, right? If you remember the history of AI, one of the first actual programs that was programmed for AI was called Logic Theorist by Alan Newell and Herbert Simon, and it was a theorem prover, and it was actually very, very good for the time. It was very successful. It proved some part of the Principia Mathematica by Whitehead and Russell, and of course it was way overhyped by the authors, as the AI tradition goes. Herbert Simon said, over Christmas, Al Newell and I invented a thinking machine. And that was the spirit of the times. People were very optimistic in the 1950s. Then it didn't work out. Then there was an AI winter. And now we are very optimistic again, I think, with some more reason for that. But anyway, as you all know, then AI and math progressed through symbolic computations, progressed through stuff like AutoMath and MITSAR and Coq and HOL, symbolic computation machines like Maple and Mathematica, but somehow it never worked, right? Never ever worked. And there is this whole field of formalized mathematics where people are trying to catch up with the math. They're trying to catch up with the actual math frontier, but in a formalized way, strictly in some proof system from some axioms. And, last time I checked, it was 2023, and the journal called Formalized Mathematics was publishing papers where people solved exercises from Sierpinski's number theory textbook, right? So these were pretty difficult exercises, to be fair, but still, they were like exercises from a 1960s textbook. So that was the state of the art of formalized mathematics. I know exactly one positive example. I don't have time to go into details, but it's the Robin's conjecture in logic and, I don't know, Boolean algebras. But it's very, very close to the axioms. Very, very close. The proof is like 20 pages of rewriting equations in equations like these ones. So yeah, okay, sure. The computer could do something like that better than humans, but nothing really serious. On the other hand, there was, of course, a huge body of work where computers helped humans by enumerating various cases, by doing computations, basically, not by proving things from scratch, but by filling in the tedious parts. The most famous example that started it all is, of course, the four colors theorem. You all know about that. The four colors theorem was already proven with the help of a computer. And then, of course, there were lots and lots of these examples, but they don't count to what I'm talking about, right? In this case, the computer the human did all the work, the human wrote the program, and the computer just enumerated some examples according to a fixed algorithm. That doesn't count. What we would like to have is a machine where you put in the theorem statement and it gives you the proof, right? Okay, so what now? Let's jump over 40 years of history, and let's go to modern AI. Let's see now, with modern compute, how do AI systems help with mathematics? And here there are two different kinds of approaches. I will begin with the reinforcement learning-based approaches, where you are like training a specialized system that specifically to do math, or even more specifically to do the kind of math you want, right? And then I will go to LLMs that are much more general. But first, let me say a few words about these RL-based approaches. So again, I don't have time to introduce reinforcement learning to you. I hope everybody kind of has an idea of what it means. And everybody has heard of the alpha series of models from DeepMind, like AlphaGo, obviously, that started it all, then AlphaZero, AlphaStar, AlphaDef, whatever. What we are interested in now is the alpha tensor model and its continuation AlphaEvolve, which we'll get to a little bit later. So what did alpha tensor do? Well, it was a very specialized system, actually. It was a system for discovering matrix multiplication algorithms, right? And again, I don't have time to explain in detail, but I hope everybody had a computer science and algorithms class, and everybody understands that matrix multiplication is basically, a relatively small-scale combinatorial exercise. And it's kind of unique in this way, because if you discover a new way to multiply 4x4 matrices, that generalizes to arbitrary matrices, because you can do a block multiplication and you can plug in your algorithm and everything becomes faster, right? So you can actually, to improve a matrix multiplication algorithm, you need to discover some very clever scheme for some fixed dimension, for some fixed relatively small case. And that's where alpha tensor came in, and they treated it as a game. It was basically the same engine as AlphaZero, the same algorithm as AlphaZero, where the move is some elementary computation like this one, and the end result, the end state, is multiplying the matrices. And then you train with all of Google's compute for a long time. I will not discuss the model in detail, and it actually improved some bounds in some cases. It was not a huge breakthrough everywhere, but sometimes it made some improvements that, of course, would have been remarkable results if they had been invented by humans, right? Then there were other models like this. For example, alpha geometry. I won't go into detail, but alpha geometry is like the same kind of machine, but for solving Olympiad-level high school geometry problems. In geometry problems, the easy part is deriving everything you know from a given construction, and the hard part is inventing a new construction, right? So the easy part is filling in all of the angles and distances and everything, and the hard part is, oh, I need to Okay, I need to do this line which is perpendicular to this line over here. Okay, so in alpha geometry, the easy part is done, of course, automatically by a fixed algorithm, and the hard part is done by this reinforcement learning-based procedure that learns to introduce new constructions. Okay, so then, and now this is what this is the important part, and then in 2024. DeepMind actually built AlphaProof, right? So this time, they actually introduced an LLM inside. I'll go to pure LLMs later, but this is already a reinforcement learning kind of model with an LLM inside, where the LLM serves as a formalizer. It translates problems set in human language to problems set in formal Lean language. Lean is one of the proof assistants, one of the most popular proof assistants. And then here is the interesting part. Then Lean cannot prove them. It's too difficult, right? The proof assistant by itself cannot prove it. But what you can do is, okay, so this is the formalizer. But what you can do is you can train a reinforcement learning-based system to help Lean prove it. Now, it still is kind of a game. It still is AlphaZero style. But the move now is a tactic for proof, right? And the tactic is something like, let's reason by contradiction from here, or let's combine this and this. Let's apply the excluded middle from here. Okay, and then Lean picks up on this and then can derive whatever it can. And probably it cannot prove it in one go, but then you make another move, right? So this is how AlphaProof worked. And again, I will skip all the details. I don't have time. But in 2024, it was big news because AlphaProof together with Alpha Geometry got to silver medal level on the International Math Olympiad, right? And like 1 point short of the gold level, of the gold medal level. Okay. But when you look deep down into this AlphaZero style protocols, you realize that it still looks kind of like, you know, very smart case-by-case enumeration. It looks a little bit parallel to, I don't know, alpha-beta search for chess, right? Like when people had been telling you for 20 years that chess is this very human game, and if computers ever learn to play chess, then we'll have AGI. And then somehow DeepMind happened, and it beat humans at chess, and nobody said that it's an AGI, right? Everybody said, well, that just means chess is easy. So if these systems, my bet is if these systems ultimately succeed, everybody will say, oh, okay, then math was easy, right? But anyway, this is one approach. And where are the LLMs themselves? And here is the thing. So in this part, my main message is LLMs have learned to do math very recently, much more recently than they appeared. And LLMs have learned to do math mostly by reasoning. I will say a few words about reasoning. What is actually staggering, what is actually exciting about it is, again, the rate of progress. So I will emphasize the rate of progress for you here. Okay, so LLMs, so first, as a little bit of an aside, mathematics is a very good subject, a very good area for LLMs. Why? Because to train a very smart, okay, so to train the basic LLM, you just need a lot of text. You just cut it in half, predict the next token, that's your training set. But if you want to train it to do difficult things, it would be great to have a supervised dataset, a labeled dataset for supervised learning. And in math and in coding, these are the two areas where we can actually produce endless amounts of syntactic data. In math, you can take a simple problem, you can change a few numbers, here is a new problem, right? And then you can even do like simple theorems that you can prove formally with Lean, and now you know that the proof is correct, and here is your training sample, right? So math and coding are special areas for LLMs, and for modern AI systems, they are a bit easier than something else. Because if you want to train an LLM to do good poetry, how do you evaluate it, right? You need good poets to evaluate. In math, it's a little bit easier. But still, attempts to make LLMs do math at first were pretty pathetic. So back in, say, 2022, when GPT-3 already existed, ChatGPT almost existed, and everybody was very excited already in the AI community. Someone, I don't remember which lab it was, did special fine-tuning for math. They fine-tuned GPT-3 to do math, and here is what it could do. At the time, it was extremely impressive. At the time, I will show you what basic LLMs could do. Then, again, math problems were kind of the first field where LLMs learned to use tools. And this is very natural because an LLM, just like ourselves, an LLM cannot multiply big numbers. An LLM cannot run an algorithm. It's just a few dozen layers. It does not have a loop inside. It cannot do, it cannot even do long division, right? It doesn't have the machinery to do that. But of course, it has the machinery to pose the long division problem and then say, run a calculator for me. So this is how LLMs use tools, and obviously the ultimate tool is a Python interpreter. So you just write code, and then you execute the code, and you get the results. And this was already happening in 23. And by now, of course, all of you use Claude Code and GPT codecs, and this is exactly the kind of tool use that has emerged into agentic LLM-based systems. And then what started to happen back in 23 and 24 were, I won't go into details on that one, but were systems where this kind of like LLMs were plugged into some kind of evolutionary learning system. LLMs were a component, a major component, a very important component, but still a component of a bigger system where you would evolve stuff. Like in this case, an LLM would write programs like the one on the right for enumerating some special cases or something, and then these programs would somehow make partial progress, and an evaluating system would tell the LLM, okay, this one made a little bit more progress. Please do more like this. And the LLM would do more like this. So systems like that were already, in 23, starting to prove relatively interesting mathematical results. Okay, so Terence Tao was very excited already 3 years ago. You all know that he is very excited about AI, but it actually started back then. So I made this picture in early 24, 2 years ago. And 2 years ago, it looked like, well, LLMs and various AI systems in general can help you, can help a mathematician basically every step along the way, right? They can help generate ideas. And I didn't talk about this, but there were interesting works where you use machine learning, not even LLMs, just machine learning to mine for patterns that could mean new mathematical results, right? Like you have a lot of numbers, you find some structure, it won't give you a proof, you have to do the proof yourself, but it will tell you where to look, what to look for, right? You can automate case-by-case analysis, you can do proof assisting, etc., etc. And of course, LLMs already could help you write the papers, right? But at that time, there was no end-to-end system that could, prove a new theorem, that could write a paper from scratch. That was definitely not possible 2 years ago. Well, let's see what has changed. What has changed most with LLMs themselves was, of course, reasoning, as I already mentioned. And I always start talking about reasoning from this slide to emphasize again for you the rate of progress. I think this is an excellent illustration. Just if you have one takeaway point, let it be this. This, in 2022, this was the original paper that started chain of thought prompting. Okay, back then, in those olden times of 4 years back, people did like few-shot prompting. No, I have 10 more minutes. I mean, I'm following. People did few-shot prompting where you would give a few examples, right, and then the LLM would kind of, set its mind to doing the kind of work you want. And this was the original paper where people realized that if you explain a solution in detail in these examples, then the LLM will explain the solutions too. This is not surprising. The surprising part was the end result would be better. It would get more problems correct. But what I want to tell you on this slide is, back in 2022, 4 years ago, these were the problems that LLMs failed at. Okay? These were the problems, like Roger has 5 tennis balls, he buys 2 more cans, each can has 3 balls. How many balls does he have now? These were the kind of problems where LLMs had trouble, and chain of thought prompting helped solve more of problems like this. This was the data set. And this was 4 years ago. And we will see in 5 or 10 minutes what is the state of the art now, right? Okay, then I won't explain the reasoning. It was a very interesting research, but ultimately, of course, it came to the reasoning models we know now, right? So the reasoning models where an LLM has a hidden scratch pad, it writes down its thoughts, and then it uses these intermediate thoughts to formulate the final conclusion. So by now, of course, for a year already, everybody has reasoning models. We all use reasoning models. It's not news anymore. Okay, so what happens with the math? What happens with the math, and where are the LLMs now? Well, I will mostly skip this part. It's not really interesting, but let me just say that all of the benchmarks begin to saturate. Okay, there was this famous math benchmark that was very difficult for GPT-2, quite difficult for GPT-3, and now it's completely saturated. It's like 98, 99%. There is no point in comparing on this benchmark anymore. There is a much more difficult benchmark that you may have heard about, made with real mathematicians, called frontier math. And now this is still difficult, but again, the rate of progress is pretty staggering. So here is an example of a problem from frontier math, and I will not make any attempt to explain it to you. I wouldn't be able to. Here is the answer, if you'd like. But the point of frontier math is to make something really, really difficult, but still solvable, right? And back when it was introduced, over here, no LLM could do anything at all. No LLM, like 2% performance. And by now, we've got like 50% performance. And that's on tier 1 to 3, and tier 4, which is the hardest, and which was strictly 0 back when it was introduced. Now it's already seeing some progress. Not 50% yet, but some progress. Okay, I will definitely speak this. Yeah, and you've all probably heard that on IMO 2025, now OpenAI and Google models solved 6 out of 7 problems and made the gold medal level now as LLMs. One thought about this. There is an important difference between alpha proof and this result. Alpha proof that got almost gold in 24 and this result in 25, because alpha proof is a specialized system that you train for millions and millions of dollars, and that you run for days. It took like 3 days to work on IMO 2024. And it's specifically and it uses Lean and everything, and it's a whole system. You definitely cannot run it at home. This over here is an LLM accessible to everybody. So, okay, maybe it was not yet published at the time. By now, I'm sure it was like GPT 5.4 or 5.5, right? So now it's definitely accessible to everybody. So, big difference. And to conclude, can LLMs do math? What are the current examples? I will briefly go through the examples. I don't have time to discuss them, but I do want to highlight them, right? So first, there are a lot of multi-agent systems where lots of LLM agents collaborate with each other. And the interesting part about these systems is that you don't need to do any AI to create them. The AI is in the LLMs. And here it's just, a system of chats where LLMs can talk to each other, and tools like Google search and archive search and stuff like this. That's it. And then they help with difficult research problems. They introduce new ideas. There have been a lot of examples like this. AlphaEvolve, a good continuation of AlphaTensor and AlphaProof and everything, but now with LLMs, and now much smarter. And it already not only improved matrix multiplication algorithms, which it also did, but it actually proved a few results in mathematics itself, right? It improved it made a new lower bound on the kissing number, how many spheres can touch a given sphere, improved a few bounds, etc., etc. This was big news. Sorry for the Russian letters, forgot that. It was big news a year ago when an LLM agent, AI scientist, actually wrote a paper end-to-end that got accepted to a workshop on ICLR 2025. And of course, every human in the room said, oh, come on, that's a workshop, that doesn't count. Of course, every human would say, oh, come on, everybody, any crap gets accepted to workshops, right? That doesn't count. Wait, what about the main track? Can you get a paper to the main track? And of course they did. Not exactly them, a different team, but a different team got a paper accepted to the main track of ACL, which is like one of the primary conferences on AI, also in 2025. So I don't have time to discuss the paper itself. It's actually very instructive to discuss, but if you want, you can ask me a question afterwards. So this is the world we live in, right? AI agents already are writing papers end-to-end from scratch, from a prompt like, do something in AI safety. They go and they do it. This very interesting thing, also a kind of AlphaEvolve style system. You give it a benchmark, it goes out, it reads papers, and it tries to improve the benchmark. So all it needs is a measurable score. And then it tries to improve this measurable score. And basically it does. So of course it doesn't succeed 100% of the time, but in many interesting cases, it introduces new ideas, it combines old ones, and it actually produces new results. It beats the benchmarks. And including in math. Okay, including in theoretical computer science. I'm skipping all this. Final points. And finally, so which is probably most relevant for everybody here, finally, just user-facing systems that you don't even need any big compute for, you don't even need, lots of tokens that might cost a few $100s, not even that. Just asking GPT to prove a new theorem is already starting to work. And there have been several interesting papers about this. I don't have time to discuss them in detail, but you can just Google them later. Malaven-Stein experiment in probability theory. Gödel test in convex optimization, but not doing the optimization itself, but proving theorems about optimization, obviously. Here is a prompt, and the prompt, if you read into it, the prompt is like, well, okay, so here is a paper that I think is promising to work on. Here's my idea which direction you might work on. Please work. Okay, so it sounds exactly like any of you would tell to your graduate student, right? So here is a paper that I think is promising. Go do something new. Maybe this idea may work, and then if it works, the GPT finds it. So in this test, for example, GPT solved 3 out of 5. And formalization also works better with GPT. This is a recent example. Urban got a lot of work done in formalized mathematics by just asking GPT. And basically, what he did was he just, like this Simpsons episode, he just implemented a script that just answered yes to GPT all the time. And just go on, continue. And GPT just worked through the whole set of problems. Very, very interesting. Oh, sorry about the Russian. Forgot to translate this part. Donald Knuth recently became a believer, right? You may have heard about this. Donald Knuth solved an open problem with Claude Opus that had not that had haunted him for a few weeks before. So he had actually worked on it, and he couldn't solve it, and Claude just went and solved it. Okay. Again, I recommend to read this paper. It starts with shock, and it was probably a shock for Donald Knuth, but now he is a believer. And the last piece of news, it's from a week ago. GPT 5.4 Pro solved one of the Erdős problems. GPTs have solved a few Erdős problems by now, not many, but a few. But this one, GPT 5.4, solved in a very creative way. Again, I don't have time to explain in detail, but basically it like rejected the whole premise that mathematicians thought was mandatory, and it did it in a different way. So it didn't pass to probability theory in this problem like everybody did. It did it with pure combinatorics. Very interesting. And just to emphasize the rate of progress, now we have GPT 5.5, right? Which is smarter. How many more Erdős problems will it solve? So, okay, now I'm concluding. It seems like current LLMs can already, at least partially, drive algorithmic progress for themselves based on these results in matrix multiplication, for example. Matrix multiplication is what AI is built on, right? And yes, of course, it's not yet the singularity. And yes, of course, for a few more steps like this, I will say yes, of course. But sometimes we will get a singularity out of this. Another important thought is that it's not at all necessary for this singularity to happen for AI to do everything under the sun, right? Sure, robotics is harder, right? Robotics involves real work in the physical world. It's harder probably than math. But if you can do AI research better than humans, then you can use the AI to solve robotics, right? That probably is the way it will go. And finally, a reminder of the rate of progress. In 2022, we had LLMs solve problems like 5 plus 3 times 2, how much will it be? And it was difficult. Now, we are solving Erdős problems that have been open for 50 years with some creative new machinery, and it's still not AGI. So this is a reminder on the rate of progress. And, you know, I'd like you to consider, like, where are we now and where are we going? So I made this chart a while back. It's like this creativity scale. The numbers don't mean anything, of course. But research is an optimization process. And as optimization processes go, it's of course pretty advanced, right? So the most uncreative process is of course random search. You will get a proof of everything, but it will take you a very long time. Then like gradient descent evolution, pure reinforcement, blah, blah, blah. And then there is Einstein inventing the general relativity. Everybody kind of agrees that it was the most creative work ever done, like the biggest gap from what was before to what came after Einstein, right? But I want to leave you with the thought, imagine what does it mean to be at 11 on this scale? What does it mean to be at 25 on this scale? And what will the world look when AI systems will overcome the 10 on this scale? Thank you.
Thank you, Sergey. Thank you. Okay. Thank you very much. Okay. Take a seat. Thank you very much, Sergey Nikolenko from St. Petersburg. And we heard about a timeline of the AI. And he mentioned that 2023 is the spring of AI. Some people call that way. I also like to mention that some people also call 2012 as the year one of climate AI. Because that was the year when the 3 climate giants of AI all gathered in the Institute of Pure and Applied Mathematics, IPAM, in UCLA, Los Angeles. Jeffrey Hinton, Ian Nacon, and Joshua Bengel all gathered in a summer school on deep learning, feature learning at IPAM, UCLA, where I was a part of that organization team. And actually, in China, Professor Wu Wenjun also contributed significantly in the proof of mathematical theorems, as Professor Fan Genhua knows from Chinese Academy of Sciences. Wu Wenjun was doing this in the 1980s for the machine proofs, right? He was trying to prove theorems in high school geometry. Yeah, that's in 1986. And then Professor Wu Wenjun visited USA for a few months in 1986. He visited Argonne National Laboratory to talk to the people who do the automatic differentiation. Now realize that although differentiation now is at the heart of the current neural network design. Yeah. So now let's move on to the next talk by Professor Xin Yao. And Professor Xin Yao is Vice President for Research and Innovation in Ningnan University, Hong Kong. I have a family member graduated from that university, so I'm very honored to introduce you. And Professor Xin Yao is a pioneer and top expert in computational intelligence and especially evolutionary algorithms. I heard about the genetic algorithms and simulated annealing many years ago when I was in graduate school. So I really like to hear Professor Xin Yao about what's going on in evolutionary algorithms in the current revolution of AI. So, but I like to say this AI did not start in 2012 or 2023. It has been going on for a long time. So we really like to hear what has been going on since evolutionary algorithms started some decades ago. And Professor Yao has been very successful in the IEEE community, and especially he was awarded 2020 IEEE Frank Rosenblatt Award and numerous other awards. So please join me. Welcome Professor Xin Yao from Ningnan University, Hong Kong.
Thank you very much for the introduction. Sergey gave a very good talk, and then towards the end, he said his excellence with level 1 to level 10, and invite you to predict level 11. So my talk will be at level 3. Okay, so level 3 is my talk, so that's where I am. So it's a bit of a historical review now in that sense, because all the information I'm sharing with you was still manually produced, so way behind this frontier of LLM. Okay. So my talk really has 4 parts, depends on time. One is I will say a little bit more about the evolutionary computation, although Sergey mentioned it already. And then I'll share with you my own interest. It's a very specific level 3 topic on computational time complexity of evolutionary algorithms. And then I'll explain a little bit why it differs from the traditional complexity theory in terms of what we want to do. And then I'll share with you the concept of EA hardness. EA means evolutionary algorithms. If I have time, I'll share with you what the drift analysis is. This is really a method that we use in proving some theorems. So what is evolutionary computation? So slightly formally, I said it's a study of computational systems which use ideas and get inspiration for natural evolution. Okay, so that's more like a description. So if you ask me, what do you mean using ideas or getting inspiration? So survival of the fittest is extremely simple principle, and then I'll show you how it could be reframed as a problem-solving strategy. If you look at the more applied side, evolutionary computation has been used quite a lot in optimization, in machine learning, in so-called creative design. But the creative design part has been disrupted by the most recent progresses in LLM. And then last part, in terms of why people are still interested in evolutionary computation techniques, is it's very easy to get started. It does not require very strong domain knowledge. But if you do have domain knowledge, it can be used to speed up or to make an algorithm more efficient very easily. So here's one example, survival of the fittest. This is suitable for non-mathematician like me, who is a bit slow, okay? So in terms of problem-solving strategies, sometimes you can do a very top-down way, starting from axioms and then derive some theorems. But I'm a little bit slow, then I say, if you encounter extremely difficult problem you never encountered before, I'll start with the random guesses what solutions might be. Okay, so that's very important. I have a population of solutions. And I just compare which solutions are better than others. I don't really know the correct answers to those problems. And then I select better ones, and then I have a random mutation or random crossover. That's why I call it level 3. And then I generate the offsprings. And then I select better offsprings, and then just cycle it through. So you can see I have this extremely simple algorithm where I always look at a collection of algorithms, a collection of potential solutions. And then I select better ones, mutate them, and select better ones and mutate them. Okay, so this is a little bit like a survival of the fittest. If you put in a little bit of computer science ahead, you come up with the algorithm. And I always said that this is the world's simplest algorithm with only two lines. Well, this repeat is really one line. One is generation of solutions, and the other one is really to select whether those solutions are satisfactory or not. Okay. So this is the idea of survival of fittest and how that idea could be translated into a very simple algorithms in computer science. Okay, I have 2 slides to show you what can evolutionary computation do. Some of you do know, some of you don't. In the very first ever Olympics in Beijing, 2008, we know this bird nest, we know this water cube. And then when this bird nest was first in the news, people say, oh, look, it's so beautiful, because all these structures, they're irregular, right? Irregularity is beauty, as claimed by the media. But then some engineers, or including me, thinking, if you have an irregular structure, how can you guarantee the stability of the whole structure? How? You can't just throw this real bird nest onto the ground unless you calculate the stability of the structure. It turns out the architect actually used a design tool, that tool was actually driven by an evolutionary algorithm. So this is yet another example. So this is actually the bullet train, the latest bullet train in Japan. If you visit Japan, I don't know, a couple of years ago or in the future, you will see some of the bullet train has this shape. I always said that this front is a bit like the beak of a duck. It's a very unusual shape, right? Because our intuition is if you want to minimize air resistance, you need to have a shape which is very smooth. Yeah, all the trains in China, for example, this is very smooth. You just get longer, the nose get longer the longer, but it's very smooth. Duck beak has never been well known for being, duck has never been known for being fast. Okay, it's just duck beak. And then you say, how does this shape come up with? Who dreamed up with this? And then you can dig. There's no paper, but there are technical reports floating around in the literature. It actually eventually says it used a design tool using evolutionary algorithm and try to balance different criteria in terms of writing quality, reduce noise, and consume less energy, etc. So those are 2 examples I'm going to show you. And then these examples has been shown by Sergey in terms of how evolutionary algorithms actually have been used at the different places of LLM. I'll skip this. I'll skip this part. So I want to spend a little bit time on computation time complexity of evolutionary algorithms. So if you are interested in evolutionary algorithms as optimizers, those are the three very natural questions people ask, whether you are in the domain, not in the domain. If you have optimization algorithm, the first question is, does it converge? Okay. The second question is, how long does it take to converge? I always said the first question probably more of interest to mathematicians, the second question slightly more interest to engineers, and the last one probably is of interest to engineers and computer scientists. Okay, so what's the relationship between the problem size and the computation time? Does the computation time actually scale as the problem size increases? Okay. Yeah. So just one slide about the convergence and the convergence rate. Convergence really says if the time goes to infinite, whether I can find a global optimal. Okay, so that's a very basic foundation. And then you can actually see some result. All the evolutionary algorithms with elitism, they do converge. Some of the algorithms without elitism also converge, some don't converge. Okay, so not every evolutionary algorithm you encounter literature actually converge. And then there's a question in terms of how fast it converges. It converges too slow, and then practitioners will not be very interested in it. Unfortunately, all the convergence proof in the literature are about the local convergence rather than global convergence. In terms of proving convergence, is a fairly orthodox approach. There are different approaches one can use, and then the approach we use quite a lot is really looking at modeling evolutionary algorithm as a Markov chain, and then you can establish so-called weak ergodicity of Markov chain. If you translate into words, it's very simple. If I have an evolutionary algorithm, if I have some mutation operators, crossover operators, or any search operators, I want to ensure every potential solution in the solution space has a non-zero probability to be generated. Okay, that's what weak ergodicity means. And a strong ergodicity basically says the Markov chain eventually converge to a stable distribution. It won't change, the probability distribution will not change anymore. And then lastly, if you want to make sure this converged distribution is the optimal distribution, that means the probability of finding non-optimal solution is 0. Then you prove the convergence. Yeah. But convergent people said it's not going to keep my job because I need to find a solution soon rather than until time goes to infinite. So this is where computational time complexity comes into it. The very first one, which we need to, at least I need to keep in mind, is for a complexity result in evolutionary computation, they always look at a particular algorithm on a family of problem instances. Okay, so whenever we talk about the complexity result in evolutionary computation, we attach algorithm to it. In the traditional complexity theory, when you said the TSP is NP hard, algorithm is not there. It's a description about the problem entirely. Okay, so I think that's a very important difference. In evolutionary computation, we care about the relationship between an algorithm and a set of problem instances. But traditional one, they only look at one problem rather than go into problem instances. The second one is all the complexity results in evolutionary algorithm are average case analysis, not worst case analysis. This average case is very different. It's actually fundamentally different from the average case in traditional sense. In traditional complexity theory, when you talk about the average case analysis, you assume a distribution of different problem instances. But in our case, because evolutionary algorithm is a stochastic algorithm, the average case means actually more like average time. of finding a global optimum. So a little bit formality just shows why this complexity result in evolutionary computation is different from the complexity result in a traditional sense. So if we have an evolutionary algorithm, which is fundamentally a stochastic algorithm, and then we always consider first hitting time as the time we are finding a global optimum. Because it's a stochastic algorithm, you can find a global optimum and then move away. Okay, so there's a nature of it. So whenever we talk about the convergence time now, from now on, I mean the first hitting time. First hitting time means the first time I find a global optimum. Okay, and then these minor details I will skip. And then here are a pair of questions we always ask in evolutionary computation, okay, in the area. Under what condition evolutionary algorithm is guaranteed to find the optimal solution in no more than polynomial time? Okay, so we're interested in this algorithm. Then we can say that if I use this algorithm to this class of problem instances, it's going to be very efficient in theory, because high order polynomial is actually not practical, but in theory it's efficient. On the opposite side, we want to see under what conditions an evolutionary algorithm find the optimal solutions in at least exponential time. So that would be the problem instances where you don't want to use this evolutionary algorithm because it will take at least exponential time to find the global optimal. So this is ultimate goal is actually all driven from the practice. If you have an evolutionary algorithm, you want to know when should I use this evolutionary algorithm appropriately. I heard more than one person complain, well, genetic algorithms, they don't work. I think those kind of conclusion is a bit unfortunate, and then we ought to understand a little bit more why it doesn't work, why it works. Okay, so that's precisely what the complexity analysis in evolutionary algorithm try to do. Now I'm going to, I can skip this. Now I'm going to show you one pair of results. It's not saying these results are good or not. It's really to give you a flavor what the theoreticians in evolutionary computation try to do. Okay. So the first one is really looking at polynomial average computation time. So we represent evolutionary algorithm as populations. Okay, and then each population will be represented by this Cassini T. And the D of Cassini T means the distance from my current population to the global optimum. If that distance is 0, that means I have found a global optimum. Okay, so, and then this can be modeled as a stochastic processes. Okay, we can use a Markov chain. Well, you can use other stochastic processes like a martingale as well. I think that's more technical side. So the first step is we model an evolutionary algorithm as a stochastic process, like a Markov chain. And then we describe two conditions of this stochastic process. If there exists one polynomial of a problem size, so the problem size n, this h of 0 is a polynomial, such that for any Cassini T, for any population, its distance to the global optimum is upper bounded by a polynomial. Okay, so this is what mathematics says. The second condition is for any t is iteration number starting from 0 to infinite, if the algorithm is going. If the current population is not the global optimum, because distance to the global optimum is greater than 0. Then, when we have one iteration moving from t to the t plus 1, the distance I made in expectation, of course, is lower bounded by an inverse polynomial. Okay, so the first condition says for any population, its distance to the global optimal is upper bounded by a polynomial. The second one is when you iterate from one generation to the next generation, its distance to the global optimal is lower bounded by inverse of a polynomial. Okay, so those two conditions. If those conditions are true, and I said the average time to find the global optimal is upper bounded by a polynomial. So h is another polynomial, and this is a average computation time, average represented by expectation here. So these conditions are true. Now in this algorithm I can prove it's very efficient because it takes only a polynomial time to find a global optimal. If this is slightly tricky for you to understand, I translate just by words, okay? And then it becomes very intuitive, or at least in my view. The first condition says, because for any population, it's always upper bounded by a polynomial. You can see in the entire evolution processes, okay, this population is never too far away from the global optimal. Why is it never too far? Because it's upper bounded by a polynomial. The second condition says, when I iterate from one generation to the next generation, the drift, the steps I take towards the global optimal is always lower bounded by inverse of polynomial. So you can imagine every time I will make a reasonably significant progress towards the global optimal. Then you can imagine if I have a stochastic process which is not too far away from the global optimal, and then every time I make a positive progress towards global optimal, then I take at the most polynomial steps to actually find the global optimal. So that's what the theorem says. Reasonably intuitive. And then we look at the second one of this pair is look at the exponential average computation time. So we want to understand what kind of algorithm will have exponential time behavior. So there are two conditions as well. So this looks very complicated. Maybe for the sake of time, I can go to this kind of translated part. So we also have these two conditions. One condition says for this kind of difficult problem instances by this algorithm, there's a special region, the distance region in terms of distance to the global optimal. That distance poses particular challenge to this evolutionary algorithm. Okay, because if you fall into this region, you actually tend to drift away from the global optimal rather than moving towards it. Okay. So you have this particular region. If you have this population within this region, you move away from global optimal rather than getting closer. Then you say, okay, I'm moving away. If you move away even greater than d of a, the distance is very large, then you start drifting towards global optimum. Again, you actually attract to it. However, the attracting the step is very, very small. Okay, if you have these two conditions, and then this algorithm will take at least exponential number of steps to find global optimal. Okay, in expectation, of course. Then you just use imagination. If I have a stochastic processes where if I'm very far away from the global optimal, I will drift towards global optimal. Okay, that's what we want to do. But every time, tiny steps, very small. Once we get into this region, critical region, I start moving away. So you can imagine the algorithm is actually drifting at the boundary of this DA. If you're within this DA, you're drifting away, and then when away, you come in there. And then you can imagine you will consume lots of time. That's where actually the exponential time comes from. So this is how you prove this theorem. So these slides really give you a glimpse of what kind of result one could obtain. The very first one is being cautious. If we use a stochastic algorithm of evolutionary, like evolution algorithm, which does not use a lot of domain knowledge, and then you apply to a polynomial type problem, it's possible on some classes of instances you get exponential time behavior. So that means careful selection of evolution algorithm is important. The second one says actually for polynomial time problems, you will be able to find polynomial time evolutionary algorithm. So whoever who tells you evolutionary algorithm is always slower than other competing algorithm, that's not completely true. Okay, partially true, partially false. The later two are very interesting, which actually map to our intuition. Instead of finding the exact global optimal, if you are willing to sacrifice so-called accuracy, if you find epsilon approximation to the global optimal, you can change exponential time algorithm into a polynomial time. Okay, you can make it very efficient. The second point is we always emphasize evolutionary algorithms are population-based algorithms. Now you actually have evidence to demonstrate why population is important. You can prove a pair of results. If you use a single individual population, it's not population, to solve a problem, you get the exponential time behavior. But if you increase population size to be 2 or greater, you immediately get polynomial time behavior. So this shows the power of population. Like any other cases in complexity theory, you can find the counterexamples. You can artificially create a problem which challenge this statement population is useful. Okay, so in only the 5 minutes I have, I'll explain this concept of EA hardness, EA easiness, and then drift analysis. I won't go through it. You probably think this proof method will be replaced by LLM anyway later on, if you are interested in this. So problem classification, why bother? I think that's the important part. So when we analyze algorithm, we want to know which problem instance classes are more amenable to this algorithm and which are not. Traditional complexity theory are not interested in problem classes. Okay, they're only interested in problems. And different instance classes of problem pose different challenge to different algorithms. In EC, evolution computation, we are particularly interested in problem characteristics that makes the problem hard or easy for a given algorithm. And that's why I repeatedly said the complexity notion we use in evolutionary computation is always linked to a particular algorithm. Okay, for exactly the same problem instance class, it can be EA easy if I use algorithm A, or could be EA hard for algorithm B. So we are interested in analyzing the relationship between the problem characteristics, algorithmic features. We want to match these two, and then this will really guide our design of new algorithms for a particular problem. So here's our notion of easy class and hard classes in respect to evolutionary algorithms. So if we say the problems are easy, that means starting from any initial populations, the mean number of generations needed by the algorithm to solve a problem is at the most polynomial in time. Hard class, that means as long as from some initial populations you need at least exponential time to solve a problem, then this is a hard instances. And then these slides really describe what's easy and what's hard for evolutionary algorithm. Okay, so in the future, at least you can get some ideas. And this is if and only if condition. So I think if you look at the easy classes, it's very similar to what I said. First condition is every population you encountered in the process is never too far away from the global optimal. And then every time when you make progress towards global optimal, you have a lower bounded. That means you make sufficiently large steps. For the hard classes, you get the first condition is for some population, you can drift away very far away from the global optimal. Secondly, the progress you made from 2 steps and they can be very small. And that's why you take a lot of iterations to obtain it. I will skip this and then I'll just show you my last slide. So this is really my summary slides. The message I've been said already, I won't repeat it here all the time.
Thank you, Professor Xin Yao from Ningnan University. Professor Xin Yao from Ningnan University, Hong Kong. We have time for a question. Okay, any questions from the audience or from online?
Obviously, between the time and the coffee break, everyone prefer coffee break.
Okay. So during the coffee break, we still have time to talk with the 2 speakers and the next speakers. I have a question for you to think about. So give a algorithm, we can estimate the computational time. So I'd like to see if we like to set the computational time, can we reverse it to design the algorithms? Is that possible?
At least there is a community of people are doing exactly that type of research. Yeah.
Okay. Good. Thank you. So let's have a break. So let's come back at 20. Okay. So let's still come back at 11:10. 11:10. Okay. Thank you.
Thank you all the guests. Now it is time for coffee break. Please come back in 20 minutes.
Okay.
and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. offering multiple intelligent and efficient services, connecting global academic, technical, and talent resources, connectivity, innovation, inspiration, fusion. ChaSpark website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied back propagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. ChaSpark website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. ChaSpark website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthale invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1-kilometer-long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the three laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems.
Attention all the guests, please take your seat. Our forum will continue at 11:10. All the guests, please take your seats. Our forum will continue now.
Hello, everyone. Welcome back. Now we move on to the next presentation by Professor Galina Stragova from Saratov State University, Russia. Galina has been with the Saratov State University for a number of years. She has been moved on from there, from assistant professor, associate professor, and full professor. And Galina is a top expert in neural network dynamics, complex dynamics, nonlinear physics, and applications in neuroscience and other engineering and sciences. And she has been awarded a number of significant research grants from Russian Science Foundation, especially one grant from the President of Russian Federation. And she's going to share with so please join me to welcome Galina.
So thank you very much for a very kind introduction, and I'm very happy to be here and present and to share my physical results and to show how mathematics can help resolve and solve very complex physics tasks. And so I'm going to speak about the impact of Levy noise on the dynamics of neural networks, which underline on the real brain activity. But before, at the beginning, I do believe that no and auditorium which is here. So let me start. So everybody knows and they believe that external random disturbances, especially noise, can be only destructive and can destruct the system dynamics, can induce chaos, can suppress different spatial structures, so destroy all the behavior, all the dynamics of complex systems. But from the other hand, there is a counterintuitive fact that noise can be beneficial and can play a beneficial role to induce some order and switch from irregular dynamics to regular ones and induce so when you feel and undergo some continuous stress, our brain activity can develop mental noise as an adaptive response to emotional and cognitive demands. So this is responsible for information overload, famous multitasking, and other things. Neural noise, which is also present during our brain activity and brain functioning, represent random changes which encode no information. But from the other hand, it may both reduce our ability to detect faint patterns in a picture or in voice and conversation, from the other side, to hear faint sounds and also enhance some important brain function. Such kind of mode is more realistic and more produced in realistic systems and exhibits an impulsive jump-like noise process, which is absent in Gaussian noise, and such behavior occurs in real system. For example, in climate networks, and also is responsible for such kind of effects, right? Extreme events. To have some order from chaos. These effects called stochastic resonance, coherence resonance, and also when we consider some mathematical models, we describe some very complex networks consisting of many components and nodes. We can find also different kinds of structures as coherence resonance chimeras, which are induced by Gaussian noise, Levy noise, and this noise can suppress suppress this chimera state, or for example, or for the opposite, can induce and make and stabilize these structures. Neural networks that have formed in the presence of noise, I stress these things, will be more robust and explore more states. So the presence of noise can make neural networks to be more stable in comparison with the noise-free case. So, and in this case, such networks can facilitate learning and adaptation to the changes demand of neural networks. And as a model of the individual elements of our complex networks, we choose so-called Fitzhugh-Nagumo oscillator, which is a canonical, a more realistic model which can describe a real neuron in our brain activity. So the equations you can see here, it's just two variables, U and V, and for the dynamics of in time, temporal dynamics of each variables are described by the equations first and the second one, and we consider the topology of these neural networks like a ring topology. You can see in the right picture, the controlling parameter which are used to study and to change the dynamics of the considered networks are coupling parameters, which is C, and in the 1, 2, 3, fourth term of the first equation, and the range, coupling range R, which is responsible for how many nodes are coupled with the ith oscillator in our networks. If we fix the parameter as shown in this slide, so, and we change the non-local coupling strengths fix the coupling range as this number is shown in the slide. And if the total number of elements in the network is equal to 300, it's enough to study the dynamics of these neural networks and to analyze how the Levy noise can influence this network dynamics. We add Levy noise source eta I on T to the second equation, of our network. So if consider individual Fitzhugh-Nagoon oscillator with a very famous model, I repeat one again, a very famous model for real neuron. So it governs two parameters which is responsible for the dynamics, especially parameter A, which defines the excitability threshold when each neuron can spike in subsequent moments, time moment, or if parameter A in modulus less than 1, we have a self-sustained oscillatory regime when, if you look at the right picture, this is the phase portrait on the U and V plane, coordinate plane, you can see so-called limit cycle, and when when the parameter A satisfies this inequality, center of this slide, you can see two parametric diagram when you have weak coupling and weak coupling and strong coupling, and the effective parameters which we change is the coupling strength and the phi angle phi when I return back. So the coupling terms between the oscillators is governed by the rotational matrix B, and you can see here the numbers B, and also consider it depend on the harmonic function and the angle phi. So this is control parameters for the coupling. So if you look at the arrows and the pictures, so many different structures can be observed in the noise-free case of the neural networks. So the upper figure, for example here, is a snapshot when you can see the variable value for each oscillator at a fixed moment. It's just like a snapshot at a defined time after some transient period or after the main period of differential equations. So the low picture shows the phase portrait on the U and V coordinate plane, and you can see different structures here, and I will mention some of them and then we'll give some definition. So, and different colors which show the amplitude of the oscillator and the phase portrait reproduce and correspond to different node dynamics and correspond to different structures. So in this case, we can observe so-called solitary states, also another case of solitary states, which is green, blue, and yellow arrows. Also, we have so-called chimera states. I will give the definition later. And also a very interesting structure which is observed in neural network when the structure combines both solitary states and chimera states. And this is structure we call as combined structure. So just briefly, what is the chimera states? So the first definition and analysis will be done by Kuramoto and Batantoch in their paper, and they show that when we decrease the coupling strength between the network nodes, we come from the full synchronization when all the nodes oscillate simultaneously, and at each moment they show the equal values. So, and when the coupling strength decreases, we go through the intermediate state when some nodes are synchronized, are still synchronized, but the other one are desynchronized. You can see here random behavior, like chaos, like spatial-temporal chaos. And finally, when the coupling strength is weak, you have just a very stochastic behavior, noise depend behavior, but this is a deterministic case. All the oscillators behave as in own dynamics. So we have that coherent domains of periodic in-phase oscillation can coexist with incoherent domains, and which characterized by achaotic behavior in time, in space. So this is an surprising effect was called like a chimera state, just according that this structure combine or correspond to the coexistence of different structures simultaneously. So when an array of identical oscillators is split into coexisting regions of coherent and incoherent oscillation. So we can observe both synchronization and desynchronization domain. So this is a chimera state. So what is solitary states? So when we with neighboring elements which can behave coherently or can be completely synchronized. Moreover, solitary nodes are typically randomly distributed along the network space, and their number increases when the coupling strength between the network elements decreases. So, as I said before, that there is also a so-called combined structure when we can observe both chimera state, which is shown in green, and solitary states, which is shown in red points. It is a pity, it is not very good pictures. So, and when we consider three different states, like chimera states, solitary states, and combined structure, so there is a network parameter plane when we can observe these three structures simultaneously. This effect is called as multi-stability. And this multi-stability can be observed without noise. And the realization or observation one of these three regimes depend on initial conditions. So, for example, if we change initial conditions, we can observe either chimera states, but without noise. The probability to observe chimera states is going to 0. And in this case, when we change initial conditions, we can observe solitary states with 60% probability, and the rest, 40% probability, belong to combined structure. So now the question is, what is going on with this structure, with this multi-stability regime, and which of the three mentioned regime will win and will be observed when we add Levy noise to the second equation of our neural networks? What will be? Will be mass? Will be complete chaos? Or will be some order? So experts in Levy noise and statistical physics know that just in numerical simulation, we can use the Janik-Veron algorithm to put our mathematical models the Levy noise source, and there is three main parameters for this Levy noise source, and alpha, which is a stability index, and when alpha L is equal to 2, the Levy noise generator shows a Gaussian distribution. When alpha L is equal to 1, this corresponds to Cauchy distribution. So beta is the skewness of the distribution. I will show you the plots. And finally, sigma L is the scale parameter, which is also connected to the noise intensity. And we will use this parameter as the noise intensity. So this is the characteristic, the probability density function, which show how the distribution of Levy noise change when alpha is slowed down. You can see here that Levy noise and alpha stable noise, when alpha decreases and go into the Cauchy distribution, we have a high Taylor distribution that is responsible if you see, for the temporal dependence, which is responsible for very high jumps and spikes, even very high amplitude, not shown here, and this can be responsible for extreme events. As you see in the right plots, there are three plots. When beta is equal to -1, red one, it shifts to positive noise, to the positive jumps, and when beta is equal to 1, this corresponds to the green plot. The noise intensity and noise dump shifts to negative values. So now let's add Levy noise and try to answer a question. Can noise help create order? So let's study the impact of this noise on spatial temporal patterns, which we mentioned before, and try to find out how the dynamics of neural networks can be controlled by Levy noise. But I will focus on the multi-stable regime, and of course I will use some evaluation for synchronization and order level just to estimate the Levy noise impact. So we use cross-correlation coefficient, which is defined and calculated as well. So in this case, we consider how the value of the first oscillator correlate with the other oscillator in the network when we change the noise intensity, the coupling strength, so the control parameter of our networks. So to estimate and to analyze the behavior of the whole network, we space averaged cross-correlation coefficient to have a whole behavior, to estimate the whole behavior from the statistical point of view. And finally, which is the more important, and you know from statistical physics, so the level of system dynamics complexity can be estimated by Shannon entropy. Here we use the following expression, where PL represents the probability of the event number L, which is in our consideration represents the following regime: chimera state, solitary state, and combined state. So what we observe in the multi-stability regime. Now let's calculate the probability of happening each of the multi-stable regime, which depend on the initial conditions. Solitary state, combined state, chimera state, when we vary the noise intensity, sigma L. It is quite weak noise, but it's enough to suppress or to induce regimes. So if you compare the graph, moreover, we change the alpha, the stability index, and decrease and go from the Gaussian noise, from the Gaussian distribution to the Cauchy distribution, you can see in the legend. And so you can see that when the noise intensity increase, even for weak noise, solitary states suppressed for any value of alpha. So the combined state first induces the probability of the observation increase, and then starting from a certain value of the sigma, the combined state, the probability is less or coming to 0. But what is it about chimera states? Chimera states induces by noise, because before in the noise-free case, no chimera states, the probability is equal to 0. But when we increase the noise intensity, and when we vary the stability index, we can induce chimera state and even sustain them with 100% probability. Look at the Shannon entropy. So it's the same scale as it was done for the probability of the multi-stable regime. So for the same value of the stability index. So first, the Shannon entropy decreases, so this corresponds to order in the network. But then why? Why order? Because the solitary state suppressed. So we have only two states which depend on initial conditions. So that is why the Shannon entropy decreases. Then they increase again because chimera states induced by noise, and finally, starting from some threshold, a certain noise intensity, the Shannon entropy goes to 0 when the noise intensity increases. What does it mean? So the order in the system, we observe the order in the system, in our neural network, because there is no ambiguity in the network. We have only chimera states, and no other structure can be observed. So I have, okay, I will skip the impact on solitary states and come to conclusions. So, as you can see, in the multi-stable regime, Levy noise can suppress all dynamic regime except for chimera state, which is important because it is very responsible for brain activity, for different pathological and for nervous system of cognitive function. So we can also see the dual role of noise in neural network, when noise can not only disrupt dynamics, but also excite and stabilize very special temporal dynamics, as was exemplified by the chimera states. And these results can be directly applied to the study of brain dynamics in different functional regime. And of course, our investigations, our results, can provide theoretical foundation for using targeted stochastic simulation on neural networks to suppress pathological, undesirable dynamics like synchronization or solitary states, so, or to stabilize and maintain desired operational regime, thereby offering potential strategies for neuromodulation and therapeutic interventions. So, and I think one of the outlook maybe applicable in question to the experts in artificial intelligence and artificial neural network, what is about to use a biologically relevant neuron models like Fitzhugh-Nagumo oscillator and other one, and to add some noise fluctuation, not only Levy noise, but it's a real noise sources, and to check stable or unstable the behavior and the response of the artificial intelligence of the neural network to any questions and to any prompts. So I think this is a very, very interesting and promising question, and I just welcome these experts to use this approach. So thank you for your attention.
Thank you. Thank you very much to Galina Stryakova from the Saratov State University, Russia. Any comments? As you see, we heard that combining uncertainty and nonlinearity in neural networks may lead to therapeutic procedures for brain diseases, for example.
Yes, you're right.
Okay. Yeah.
I was just wondering about the relationship between what you were talking about to sort of more computer science neural networks, right? Because these are the systems that sort of inherently explode, sort of have limit cycles and sort of typical dynamical systems properties. If you were looking at the sort of standard or any architecture of sort of computer science neural networks, like sort of sigmoid or any other ReLU functions, and consider the impact of noise on that, do you have any comments on
So in my group, we have now some experiments and some investigations concerning how noise, which is added multiplicatively or additively, can influence the learning and training effects in neural networks. And we try to use these biologically relative models just to change the sigmoid or other mathematical function, and also to add some noise and just compare the results in output of the neural networks.
So in this context, considering sort of perturbing these kind of networks with either Gaussian or more general noise, would there be any so if you use Levy noise, for example?
Yes, for example.
Would it be just, let's try it, or do you have any other fundamental principles that would drive that choice?
I think if we add, my suggestion, we check this suggestion, this hypothesis. If we add some noise, for example, Levy noise or other type of noise, so it can make easy learning and training process. It's because we shift and order the behavior of the neurons. And
then there should be also some threshold, right? I mean,
yes, some threshold. It's just under investigation, under study. Which precision, which limitation, to which threshold we can use the Levy noise, for example. If we decrease the alpha, the scale parameter, it will produce a high amplitude jumps. It's impossible. Maybe it's negative, for example, for training process. But maybe we can see an opposite effect. I don't know the answer.
So this would be just for the learning to make sure, right?
Yes.
So you wouldn't consider a stochastic neural network?
Yeah.
Okay.
Yeah. Thank you.
Thank you very much. Okay. So let's move on to the final presentation for this morning. This final presentation by Dr. Huang Yuanfei from Asia Pacific Center for Theoretical Physics. Dr. Huang was a research postdoctoral fellow at the National University of Singapore, and then a postdoctoral fellow with Professor Zhou Xiang at the City University of Hong Kong. Now, please join me. Welcome, Dr. Huang.
Thank you for the introduction. Yeah, this is Yuanfei Huang from Asian Pacific Center for Theoretical Physics. It is my honor to attend this conference. So thanks for the Kopernik Research Center and CHESPER to organize this conference. So my talk will focus on a little bit specific research area. So I will try my best to introduce the fundamental concepts and ideas behind our project. So my presentation is about the score-based particle methods for non-Gaussian systems and Levi-Fokker-Planck equations. Maybe most of the audience may not familiar with the terminologies here, so I will give some brief introduction on this. Let me start with our physical motivation. As introduced by the Professor Galina, the Levy noise is quite common in reality, such as the example she mentioned in the neural activities. My motivations comes from some non-equilibrium physics. Here are 3 examples for such systems. And the first one is a specific molecular dynamics. The name is Kimson-1 molecular. It is a specific molecular in a living cell. And it performs according to some dynamics in the living cells will perturbate by some fluctuations introduced by the molecular like water in the living cells and other living components. Because the living components of the living cells will consume energies, so these movements will introduce some other type fluctuations other than the Gaussian white noise. And this type of fluctuations is studied in such as this reference, and for in particular for this particular molecular dynamics, the non-Gaussian fluctuations is modeled by some alpha stable Levy process whose alpha stable alpha index is equals to 1.7. And the third example is a bacterial dynamics. I will recommend to remind that the pollen particle discovered by the researcher Brown many years ago, he found that the irregular movements of pollen dynamics in the water can be modeled by some random process. And nowadays we know that this stochastic process can be mathematically modeled by the Brownian motion. And imagine the scenario on a in the water other than the pollen particle. If we put some living objects like the bacteria into the water, these living objects will introduce some non-Gaussian movement, and these movements also in this reference show that they behave like some non-Gaussian statistics. And this is why we study the Levy type fluctuations. Okay, other than the physical motivation, let me move on to the mathematical modeling of such systems. Our systems is described by this stochastic differential equation. Okay, it is quite complicated. Let me introduce slowly. And xt here denotes the position variable of this particle. And b here is a standard drift. This may be model some deterministic force. For example, for the pollen particle, you can imagine if we add some other forces into this particle, it will be modeled by it will denote by this driven b. And dbt here, bt is the standard Brownian motion, and we consider the general form of this SD. So the sigma represent the multiplicating noise intensity. And this K convolution with P hat T is modeled by the interaction among many particles. Since this is also in mathematics, it's called the interaction kernel. K and PT here is the probability density of this system. And PT, the T means the time at time T, and xt is the position of this particle, and PT is the probability to find this particle at time T at position xt. And here, the non-Gaussian term here separated into small jump, which intensity is modeled by F, and large jump part is denoted by this G. And this jumps is governed by some non-Gaussian process denoted by N. And N theta is compensated in the compensator. So this is our basic model, or the general framework to describe these non-Gaussian systems. To study this stochastic process, the basic quantity is the probability evolution, which I have introduced before, this PT. And it can be shown that this probability evolution density function P hat T obeys some partial differential equation. Here we just briefly write into this form. And using some trick, we can convert this partial differential equation into this continuity equations form. And here the J is the probability current of this probability evolution flow. And Vxt is the associated velocity according to this probability column. And specifically, the V will contain the deterministic drift B, and also two components, which is quite important. And one is the diffusion score. Here, diffusion score is kind of like the gradient of some log of some probability density. And this velocity also contains a Levy score, which is developed in our previous framework. And this Levy score has a double integral form. And as an example, I only show the small jump in here. If we need to find out the large jump part, just replace this f by the large jump intensity g. The form is similar. So to find out this v is quite important because it governs the probability density flow of this system. But it is quite hard to find out this velocity field either numerically or theoretically. And this probability column, or the probability column associated with its velocity field, is quite important in other research fields. Here I mentioned the Shannon entropy to study, which is studied in stochastic thermodynamics. And we can show in our previous work that the Shannon entropy defines the stochastic the entropy production. And this production is related to the velocity field, which is introduced before. So the V is the double or the second important role here. It plays a quite critical role in defining the Shannon entropy production and also the total entropy production. So these two motivations push us to study how to calculate the velocity field V. Also, I should, because this forum is focused on AI, I should mention this framework is also related to the diffusion model, which is a fundamental mathematical model for generating modeling. So sorry, I didn't put the size, so I just briefly introduced the idea that the probability flow carries the information of this probability of the particle system. And it can evolve from a complicated distribution to a simple one. So to find out the V or find out the J, we can define or we can calculate the evolution information flow so that we can sample from a simple distribution to a complicated one. This is the basic idea behind the generative modeling. So our framework will extend this framework to a general stochastic process, because the classical generative modeling mainly focus on the Gaussian process. As I mentioned before, the PDE that governed by the probability evolution function has a continuity equations form. So this will match this probability flow with a deterministic ODE flow. And this ODE flow will be determined by the velocity field of the V in the previous slides. And here the ODE has this form. This capital XST means that the ODE start with S at the position small x at time t, will be determined by this deterministic deterministic velocity field, which is the one we defined in the in the previous slides. So the question here is that this velocity field contains the probability itself. So it is not easy to find out this function. Our problems here is to make up some solution to handle this issue. Well, our basic idea is that since this probability flow can be matched to an ODE flow, and this ODE flow is associated or is implemented by some ODE system. And this ODE system, if we can use some neural networks to construct the velocity field, and if the neural network has a well approximation of the true one, then the ODE has the similar probability flow of the original one or of the system we studied. Here, if we use some parameterized velocity field f theta and use this f theta to create some probability flow and use this probability flow compared to the original one. If these two coincide, then we get what we want. This is the basic idea behind this framework. To this end, we have do some numerical theoretical analysis for this idea. For simplicity, I will only introduce our result on this framework. So if we use some neural networks to approximate the velocity field, here we use A, P, T, theta to denote the velocity field. F theta is the neural networks, and A is the generator of the, not the generator, it's kind of like the generator of the process. A, P, T, theta has the form of the velocity field V. Then the numerical result can be approximated to PT if and only if this double integral term vanishes. And this double integral term will control the KL divergence between the numerical result and the true value. But from the computational perspective, it is quite hard to consider the problems on the whole time interval. So to make this problem easier to solve, we break the whole time interval into many sub-time intervals. And we consider the problems on every sub-time interval and in a time sequentially manner. That means when we want to calculate the evolution of the probability density on a time interval t0 to a capital T, we numerically break this time interval into a small n sub-time interval. And on every sub-time interval, we consider the optimization problem on every sub-time interval. And for the neural networks to training process, we need to modify our loss function from this square form into a more neural network friendly form. And the solution is quite simple. Just break the square term and to see what is important in training neural networks. And it turns out that the cross term here can be, the second term the second square term here is independent of the training process, which can be ignored during the training process. And the remaining term is the true loss function we need. So this term can be written in an exponential form. So we can use the neural networks to do the training process, because the expectation of these quantities can be implemented by some particles generated by our algorithms. Also, this is the one we need for the non-local part. So it is a similar idea to transform the non-local term into a exponential term, expectation term. So this is, if we ignore all the mathematical details, we can directly to the loss function finally. And this loss function contains by these 4 parts. The first is the neural networks part, and the second is related to the diffusion score, and the third part is related to the convolution part, or the interaction term part. And the last 2 is related to the small jump and the large jump part. So our algorithm will run in this scenario. First, we input some or samples of the algorithm from the initial distribution PT0, and we minimize the loss function at time tk, and using the derived loss function from we get before. And then once we obtain the optimized loss function or optimized neural networks, we use this to propagate the samples into next time step, and use the next time steps samples to train our neural networks at the next steps. And we can do these procedures cycling. And finally, we do some numerical error analysis for our algorithms, and we can show that as long as the neural networks can approximate the true density or the true velocity field with the accuracy epsilon, then our numerical error can be controlled by this error and the time step in a time interval t. Here is the specific algorithm in our framework. So I just show it here to make you maybe more interested in. So the base idea is in the previous slides. Okay, now let me introduce some numerical experiments on our algorithms to show the accuracy of our algorithms. We first consider some simple example, which is a one-dimensional drug diffusion model with finite drug activity. And this is a standard example. I will not introduce the details, so we'll gain your confusions. Well, here is the evolution. Here is the numerical results of algorithms. The first figure is the numerical results of the probability evolution of our algorithms. It shows the evolution of this particle involved in time. And the red curve, the irregular red curve, is some sample paths of the system. And the white lines are some example of the ODE system. And for the second second figures, the left side is our is the Ola Maruyama numerical results of the system, and the right side is our numerical result using our algorithms. To compare the difference between our numerical results and the true density, we use the total variation distance between two distributions to see the arrows. And the benchmark here we use is the so-called Monte Carlo method. The Monte Carlo method is just the Ola Maruyama scheme to calculate the probability density function. So because the Ola Maruyama scheme is the quite normal or the quite common choices to generate the probability evolution of the stochastic process, so we use it as a benchmark. Yeah, here is the result before. Here is the total variation distance between these two distributions. It shows the stability of our algorithms. And this is a three-dimensional example for some systems used in some financial research. And we also this is some details on the choice for the parameters. This is again the numerical results calculate using the Ola Maruyama scheme and our results. And this is the total variation distance between the Ola Maruyama scheme and our algorithms. This is the example to contains the interaction kernel terms. For this interaction kernel system, we also calculate in a similar way. And this is the total variation distance between the two methods. Finally, let me present a simple example to calculate the entropy production, because this is one of the implications of our algorithms. This is an example to consider the system in a periodic potential which has this form. And we calculate this entropy production using our algorithm, and this shows the result for different choices for the parameters. And the total variation distance shows the stability of our algorithms, because when the time goes to 100 and the total variation distance still in a relatively small region. We also use other numerical methods to compute these quantities to show that our algorithms also is accurate. This is called the GMN, the Gaussian mixture method. It is kind of another numerical approach, and we compare this another numerical approach with our algorithms, and these two distinct numerical approaches gives the coincide numerical results. Okay, let me summarize our findings or our results. In second, we provide a fixed point argument that the KL divergence can be strictly bounded by a tractable sequential loss function. And then we conduct or we propose a algorithm based on this loss function, and it develop a single neural network to conduct the score matching architecture to jointly learn both the diffusion and the drum dynamics directly from the particles. And we provide some guaranteed accuracies by showing the numerical error can be controlled by the approximation of the neural networks and the timestamps. And this is what I
Thank you very much.
Thank you.
Thank you very much. Okay. So this is Dr. Huang Yuanfei from Asia Pacific Center for Theoretical Physics, South Korea. So he presented a new Levy or Lang-Gaussian score function in machine learning, in AI design. Okay, so this involved with a Levy system or Levy Lang-Gaussian stochastic system with a so-called Levy-Fock-Planck equation, which governs the evolution of probability distributions. What's a probability distribution? You think about an image, such as a medical image, or you think about a point cloud in AI agent. So a cloud means a group of tokens, for example. Okay, so this is at the forefront in when you look at the importance of Lang-Gaussian features. One question. Okay. Yeah, Johannes. Yeah.
Could you say a bit more about the fixed point argument, how you get the KL bound?
Sorry?
Could you say a bit more about the fixed point argument for the KL?
Oh, the
fixed point argument, yes.
Okay, the fixed point argument,
yeah.
Okay. Let me find out the slides. Yeah, here. Or maybe we can show in here. Yeah. See, if you, the main idea is to construct a neural network to approximate the true density or the true velocity field, right? Here, f theta is the neural network we choose, and apt theta is the velocity defined by using the numerical probability density. So this is apt theta is the velocity field actually for the numerical evolution. So p theta minus apt theta, this form, in fact, it kind of like the fixed point problem because we want to find out the this loss function equals to b0. So that is we find a velocity field to satisfying this loss function equals to 0. This is a point view from the fixed point problem.
Okay, good.
Thank you.
Good. Thank you very much. So we conclude the morning session for this Kopernik Forum. And in the first presentation, we heard from Sergei Nikolenko from St. Petersburg about AI in mathematics, history, background, and the future. And we got inspired about what we're going to see and what AI can do for us and what for mathematicians, for scientists. And then we heard about the evolutionary algorithm, which came from a previous stage of AI, but it is still shining in the current stage of AI. Now, the last two talks by Ganina and Dr. Huang, we see that the importance of Lang-Gaussian fluctuations in data. Now, Gaussian distribution means I'm standing in the middle, so I'm under the light, so you can see my face very well, right? So Gaussian distribution means you concentrate in the middle when everything is clear. You can see my face, right? Also not very handsome. But if there's someone in the background holding a gun pointing at me, which information is important? If somebody over there but is pointing a gun at me, but you focus on the mean, focus on the middle. So you think this is important, but which one is more important? As you saw from the White House correspondence dinner party 2 days ago in the White House, you see, there's a guy, there's someone over there. So that means in some situations, maybe in many situations, the data from a far off range in the non-local area is more important. So in that case, non-Gaussian modeling is very important. And I hope this morning session, especially the talk by Galina and Dr. Huang, told you or reminded you this importance. Thank you very much, and I enjoyed it. I hope you enjoyed.
Thanks all the guys. We warmly invite you
In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chaspark website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1-kilometer-long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chaspark website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chaspark website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, mathematical principles of natural philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1-kilometer-long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied back propagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied back propagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687,
Ladies and gentlemen, please take your seat. Our forum will officially begin at 2 p.m.
Okay. Okay, welcome to afternoon sessions. And okay, each talk has 30 minutes. So if the speaker wish to have a discussion, you should leave a few minutes for answering the questions. So I will try to remind you at the last 3 minutes or something like that. Okay, now our first talk this afternoon is Jong-Min Park from Asia Pacific Center for Theoretical Physics. And Dr. Park obtained his PhD from the University of Seoul in 2019 and held a research position at the Korea Institute for Advanced Study in Seoul until 2022. And then he moved to Asia Pacific Center for Theoretical Physics as a leader of the junior research group. He's currently leading a research team working on statistical physics. Now let's welcome Dr. Park.
Yeah, good afternoon, everyone. Yeah, thank you for a kind introduction. And I'd like to thank the organizer for giving me this opportunity to attend this nice, wonderful workshop and give talk on my recent work. I'm Jong-Min Park from Asia Pacific Center for Theoretical Physics, or APCTP. And the topic that I'm gonna be presenting is about how to use some machine learning technique called legible computing to solve some long-lived problem in physics. That is the discrimination between chaos and noise from time series. So before I will talk about the main part, I would like to introduce briefly my center. The APSTP is located in Pohang, South Korea. So we have two scholarship programs. One is the Junior Research Group program, and which is designed to give some young researchers to have some opportunity to operate their own research group. And the other one is the Young Scientist Training Program, which is designed to training some independent postdoc. Yeah, so we have many researchers working on the diverse physics, especially the theoretical physics, like the high energy physics, astrophysics, plasma, something like that, including the statistical physics. And those are the older researchers in our field who are studying statistical physics. So now I'm leading one JRG group, and I have 4 postdocs, including the Dr. Yuan Fei Huang, who is sitting there. Yeah, and he gave a talk in the morning session. Yeah, and so actually my research field is the non-equilibrium statistical physics. So usually when I attend some conference, I introduce myself as the pure theoretical physicist, but I think I cannot say I'm pure scientist here because most of you are mathematicians. Anyway, yeah, so my main research topic is thermodynamics in microscopic systems. And a few years ago, I started to have interest in some other topics like time series analysis or some organization of some ordering in non-equilibrium systems like synchronization of oscillators and some opinion dynamics. So actually, when I was invited, I hesitated to accept the invitation because my research field is quite far from AI or the machine learning. But fortunately, very recently, I studied something related to using some machine learning techniques. So now I want to talk about that topic. Yeah, okay. So let's begin. So in science, yeah, what we usually do is we observe the system and obtain data, right? So sometimes it doesn't show some clear and smooth behavior, but it may have some very irregular patterns, right? And which are usually regarded due to some noise, right? But sometimes, even though there is no noise, the system can exhibit the kinds of irregular behavior, and that kinds of systems are chaos systems. Yeah. So to understand to develop the proper model to describe the interesting physical phenomena, we have to distinguish that irregularity is come from whether noise or chaos, right? So it is quite important question, but it is not easy because some noises pretend as if they are chaos, yeah. And some noises share many similar behaviors. So one example is actually the textbook said the two typical characteristics of chaos system is that they have positive Lyapunov exponent and finite correlation dimension. But so you may think that so if we measure those quantity, then we can easily identify whether the given time series is chaos or not. But that's not, because it has been reported that even for the noise case, if we measure the Lyapunov exponent, sometimes they give a positive value. And also some noise system may yield a finite correlation dimension. Yeah, so this, I mean, the direct measuring of this quantity sometimes fails. Yeah. So to overcome this difficulty, people invented several methods. Yeah. Actually, I don't have enough time to explain all of them, but some of them based on the idea that if we count some kinds of specific parents of the time series, so if the time series is originate from noise, then probably all the possible parents may appear equally likely, so that if we measure something like the degree of disorder of that pattern distribution, like the entropy or the number of forbidden patterns, then probably by using that quantity we may distinguish the chaos and noise. Yeah, and others are also similar to that kinds of idea. So, but the problem is that those methods is only justified by some empirical evidence for which is tested to some specific sets of chaos or noise systems. So it is still some possibility that some kinds of time series may violate those typical behavior. And in fact, for some tests, the counterexample have been reported. So we need another method which is based on the fundamental difference between chaos and noise. So some people have focused on the difference of between chaos and noise, which is the chaotic systems are anyway the deterministic, yeah. But if the system has noise, they are stochastic. So some method focused on that difference. So the one idea has been developed that here they check whether we can predict the next step, next value of the time series. So if this kinds of short-term predictability is possible, then we may say that yeah, this time series may originate from some deterministic dynamics of the chaos. But if it is impossible, then we can say that it is noise. Yeah, this one approach. The other approach is that here the people consider that in the deterministic system, if we see the flow, I mean the difference of the difference of the point in the phase space, then the neighboring points may be aligned along some similar direction. So if we take the average of them, then they give us some similar direction. So by discretizing the phase space, and then calculate this average flow at each discretized site, we may draw this kinds of flow map. And so if the system is in chaos, it must be show some kinds of smooth and have some global fat pattern, right? But if the system is noise, then because all the points would be pointing the randomly, yeah. So after the taking average, they did not have any clear. They did not exhibit any clear patterns and yeah, no smooth passes. Yeah. So this kinds of approach is called short-term predictability test, and this kinds of it is called the test for determinism. But the problem is that if the dimension of system is very high, then we need much larger number of data to apply this method. So it is very difficult to apply this method for the high dimensional system. And also, sometimes we cannot access all the information of the system. For example, if our system is described by, let's say, the three-dimensional equation of motion, but sometimes we can only observe its behavior along some specific axis, right? So sometimes we may access only the scalar time series. Yeah. So in that case, also we cannot apply this method. And to compensate the loss of information, we have to consider some embedded dimension created by some time-delayed time series to use the Taken's theory. So by using that, so by considering the kinds of embedded dimension, we have to apply this method in that dimension. But the point is that it has been reported that if we choose the wrong dimension of that embedded space, then it may also give some wrong answer. So it is still some questionable how to find the proper embedding dimension to apply this method for the scalar time series. Yeah. So for now, I introduced the why this problem is interesting and challenging. So by the way, after the development of AI and machine learning technique, some technique called machine learning computing, reservoir computing has been developed and draw many attention because in this paper it has been reported that if we use this reservoir computing and if we train this computing to predict the next value of a certain system, then it is found that even for the chaotic system, it can predict. It can do the long-term prediction. Yeah. So this figure shows that this figure A is the time evolution of y of x in time, which is governed by this equation motion. So this is well-known chaos system. And this B shows the time series generated by the prediction of well-trained reservoir computer. And this panel C shows the difference or error between the true and predicted evolutions. So it's very strong. Surprisingly, you can see that even when the time is 2 or 3 in terms of Lyapunov time, yeah, it shows very good prediction. Yeah. So that's what we unexpected, because we always believe that the chaos system does not have long-term predictability. Yeah. So after this discovery, now people use this the reservoir computing model to study the time series obtained from chaos systems. But interestingly, this model has been used to solve this problem, the discrimination between the chaos and noise. So that's my motivation to study this research. So now I plan to apply this reservoir computing to solve this problem. So as a trier, so I considered, I just applied this reservoir computing to do some short-term prediction test. Yeah. So in this test, in reference, actually there are two types of short-term prediction. One in type 1, we give the current position and then ask the model to predict the next position. Yeah. And the type 2, we give the difference at current time. So the delta xt is the xt plus 1 minus xt. Yeah. So by using this input, we ask the machine to predict the next difference. Yeah. So to test how it works, so as a trier said, we consider the 3 time series. One is the chaos Lorentz system, and the others are Foucault noise and uniform noise process. So in this process, the noise has very long time correlation. In this process, all the random numbers are independent and identical, so it doesn't have any time correlation, and also it is bounded. So yeah, so what we expected is that at least for the chaotic system, the reservoir computing can very well predict, even without any explicit embedding dimension, because actually, yeah, I'm not the expert in this field, so I could not explain the details. But the main point is that in the training, and during the training, actually the state of reservoir computing is updated by this update rule. And if you see here, the next state is also depends on the current state of the reservoir, the hidden node of the reservoir computing. So that means it has a memory. Yeah. So apparently what we do is we give the current position and ask the machine predict the next position. But to do that, it exploits all the information of the previously given input values because it has memory, right? Yeah. So we expect that so by exploiting all those information, the machine itself can find the proper embedding dimension to guess the next value. Yeah, that's what we expected. So even though without explicit embedding dimension, yeah, it can predict the next point from the scalar time series of some multidimensional classical chaos system. That's what we expected. So this is the results. So here the x-axis shows the true value of the time series, and y-axis shows the prediction by the trained reservoir computing. And first, if you focus the blue symbols, which is represents the results from Lorentz system, then you can see that very perfect correlation. Yeah. So as we expected, it shows very good discrimination. Prediction power. But the problem is that here, if you see these red symbols, which is obtained from Foucault noise, then you can see that even though it is generated from noise process, it has very strong correlation. Yeah, that's because it has very long time correlation. Yeah, that means, for example, currently if the noise is 1, then it's more likely to be for the noise to be 1. The next step, right? Because the correlation is very strong, right? And also, since the machine knows all the information of the previous noises, so yeah, it can, and somehow it can predict, the next value. That's the problem. And in the difference to different tests, actually, this problem has been solved, but in this case, the uniform noise now have some correlation. The reason is that if we consider the difference, then even though each noise are independent, but if we take the difference, then they have some correlation, the negative correlation, right? And also in the uniform noise case, they takes a very limited value between -1 and 1. Yeah. So by using that property, the reservoir computing can predict the next value. Yeah. So that's what we desired, right? So what we expected is for the chaotic system, they show very good prediction, but for the noise system, they do not predict anymore, nothing. Yeah, that's what we expected. So that means so the prediction power of the reservoir computing is so high, and the tasks are too easy for the reservoir computing, so that even they can predict even noise. That's the problem. So what we have to do is we have to consider some more difficult task, so that it cannot predict noise, but if it is too much difficult, then it can even fail to predict chaos, right? So we have to find some task which has some proper difficulty. There's the problem that we want to solve. Yeah, so to do that, to solve that problem, so we have came up with the cross prediction scheme. So this is very simple. So in this scheme, what we do is we use the value as an input, and then we train the machine to predict the next the difference at the next step. Yeah. Then very surprisingly, the result shows that for the chaotic system, they still show very strong prediction power, but for the stochastic system, it couldn't predict, the next value. Okay, it seems very nice, right? But we have to check whether it is universal for other, processes, right? Because we only tested it for these 3 processes. So we consider the diverse, the well-known class, the chaos processes and noise processes. Yeah. So some of them are discrete maps, and the others are continuous processes. And also for the noise, we consider the various types of noise with long time correlation and very large, fatal distributions. Yeah, and also some they also have very long time correlations. Yeah, so this research shows that to evaluate the prediction power, so we use the coefficient of determination, which is defined by the Pearson correlation between the true and predicted value. So the result shows that for the chaos time series, they shows very good prediction power. Yeah, and for the noise, the R-square takes between the 0 and 0.1. Yeah, so they are very well distinguished. Yeah. And I want to give some remark on a few cases. For example, actually in the two age class model, actually this model is known as some typical model which shows where the traditional short-term predictability test fails. Yeah, because this model has some fragmented strange attractors, or in different system parameter, they show some long periodic strange attractors. So due to this property, it has been known that the traditional short-term prediction fails to detect this system, identify this system, and so some modification would be required. But in our case, even though without any modification, it clearly identify that this process is chaos. And the other thing is that this NF kappa B model is the 6-dimensional system. But here during the training, we only use the time series of this single variable. So even though the original system is quite high dimensional system, we found that I mean, even though it is slightly lower than 1, but it still shows very good, yeah, result. Yeah, so yeah, it works very well for very diverse systems. Then why it is so successful? So so our intuitive explanation is that to predict the next difference, the difference at the next time, the machine first have to predict the next point, next value, and then simultaneously it should predict the flow at the given point, right? So in that sense, this cross prediction asks the machine to pass the short-term predictability test and determinism test simultaneously. Yeah. So if some processes does not pass either this or that, then yeah, they are filtered out as the noise process. So we think that due to this reason, it can successfully suppress the Sproul's correlation arising from noise. Okay. Yeah, actually, this is the final result. Yeah, so we tested our approach to the empirical data obtained from various sources. So here, the blue symbols shows the data obtained from some previous researchers where they identified that those time series are chaos, and this red symbol shows the reference, the time series, which has been identified as noise by using different method. So it shows that I mean, our method also, I mean, yeah, some consistent results with previous study. And before I'm talking about what is the meaning of this gray symbol, I want to give some remark on this Schwarz circuit experiment. Actually, in this time series, it is rounded up this first decimal point. So the resolution is very poor, right? But even though in that case, it shows quite reasonably high correlation. So we believe that this result shows the robustness of our method against the resolution of measurements. Yeah. And also this Parkinson tremor data, actually, when we obtain this data first, we obtained this data from some paper which claims that this Parkinson tremor time series is stochastic, but when we apply our method say that it is chaos. So we was very impressed, but after that we found that there is some ongoing deviation, debate on whether it is chaos or noise. So in this context, I really believe that our method supports the claim that
you have 3 minutes.
3 minutes. Okay. Yeah. So this is the summary. So in this research, I tried to distinguish the chaos and the noise from time series. So by using the reservoir computing and cross prediction scheme, we obtained this very nice results. Yeah. Thank you for your attention.
Okay, we have 2 minutes for questioning. Any questions?
Hi, thanks for the talk. I probably have too many questions, so I might have to talk offline. But the main one is you're focusing on identification of chaos.
Yes.
Right? Why is it so important, first of all, like to looking at the really trying to figure out whether or not it's chaotic? Because in general, strictly proving that something is chaotic is very hard.
Yeah, right. But for example, if you want to develop some model to describe some given phenomena, then actually you may consider some high-dimensional chaotic model or low-dimensional stochastic model, and both of them can generate seemingly similar result, right? But sometimes they miss some physically important information if we choose the wrong description, right?
But in this method, for example, when you're looking at identifying chaos by looking, for example, at Lyapunov exponents, right? Part of it. How do you distinguish a system with a chaotic system with a system that has intrinsic unstable direction, sort of unstable manifold? How would you distinguish between those two systems using your methods? Because I suspect that you wouldn't.
I think our method are still working even when the system is away from the stable
so that's what I mean. So for example, a system that is not chaotic but has unstable directions. How would you distinguish using your methods the chaotic dynamics or sort of pseudo-chaotic dynamics from a dynamics that just has unstable directions and is not chaotic?
Yeah, actually, basically what we are doing here is the precisely speaking, we are distinguishing whether the given system is deterministic or stochastic, right? So even though the system is unstable rhythm, if it is deterministic, then our result will give the answer that it is in this rhythm.
So it would be mostly about whether it's deterministic, not because you were specifying the chaotic part there. That's why.
Yeah, I told in that way because in usual case, if the system is not chaotic, then distinguishing the usual deterministic dynamics and noise process is quite easy. Yeah.
Well, yes and no, because for example, if you looked at even like say a chaotic system, but if you're in sort of experimental situation when you sample with sufficiently coarse time step, I suspect that you would also have a problem distinguishing between chaotic system and the noise, if you see what I mean. It might be worth trying. That you just take a chaotic system, a known chaotic system, and then use a technique by sampling it at an increasingly large time steps and see whether or not at some point your classification classifies a deterministic system as, sorry, a chaotic, well, whatever. What is attributed as chaotic as to something that is identified as a noise.
Yes, that's right. So actually it depends on the quality of data, of course. And there is not the limitation of my model, but the limitation of all the data-driven models. Yeah. So we need the well qualified data, of course.
Thank you.
Yeah, thank you.
I think time is out. So you may not know. It's okay. It's discussed in the coffee break. We have more time in the coffee break. Okay, next, our next speaker is John Hannes Zimmer, Professor John Hannes Zimmer from Technical University of Munich. And he's a professor at TU Munich and the chair for analysis and modeling. His research areas include dynamical systems and differential equations, and also the engineering mathematics. So now let's welcome Professor Zimmer.
Thank you very much, in particular to the organizers for putting together this forum for interdisciplinary exchange and exchange across continents. That's quite wonderful, I find. I want to talk about physics-inspired learning. So I want to learn collective evolution from particles, from particle data. And it is an interdisciplinary collaboration. So there's Celia Reiner at UPenn in applied mechanics. We started many years ago looking at structures, and then Nicholas Dill got involved, a close colleague of us, and number of students, a fair number of them actually originally from China. And what we want to do is look at dissipative systems which describe the collective motion of particles, and we want to learn the system from having particle data. So, in pictures, what I want to do is the following. I say I have some stochastic system where I have particles and they do something stochastic. One thing which we will do in particular is we say we have particles, they live on a lattice, and then they jump in a random manner. Yeah? So there are some jump rates, and what I have in mind is, for example, here one configuration with a finite number of boxes. You can somewhat guess a macroscopic profile. The situation we are interested in is the following. Suppose now I take twice as many particles, twice as many boxes, I scale appropriately, I still want to get the same overall profile. And then I'm interested in how does this curve evolve in time. And that's what I want to learn from particle data. And so it's about learning collective evolution. It's, if you want, learning PDEs, or initially the transport coefficient of PDEs. And I will put particular emphasis on the structure of the PDE. So I'm not per se interested in learning the evolution alone. I want to understand the structure of the evolution, and that will be a thermodynamic structure. So I will use physics-informed learning, namely thermodynamic principles. And that requires a bit of theory, I'm afraid. So I try to give the description of the physics behind what I'm going to do here. So I want to learn evolution, and I want to learn the thermodynamics of the governing system. What is, in a physical sense, a sensible thermodynamic system? For systems which diffuse, a natural system, a natural quantity to look at is an entropy. And later on, one task will be, can we learn the entropy? So that's half of what we want to do, learn what the entropy is if you give me particle data. The other half is, what is the governing PDE? And I write it in a slightly funny way. Namely, I say I have some state variable z. And here I write it deliberately in an abstract way. Z could be a vector, Z could be a complicated object. In the applications I'm going to show, Z will always be the density of particles, something simple. But in principle, what we develop applies to more general systems. And here comes half of the trick. We describe the macroscopic evolution, the collective evolution of particles, by saying the entropy is evolving, namely specifically the gradient of the entropy, in such a way that the evolution of the system, the time derivative of z, is given by some operator k acting on the derivative of the entropy. And I claim, well, actually other people who have developed this claim that this is a relatively general framework. It's sometimes called half of generic. So it's kind of saying if you have a system which has no conservative part, then I can write the PDE in this way. And I admit this looks weird, but it's really important, since what I want to do is two things: learn S, and second, learn K. So to familiarize you with these structures, let's do the simplest possible example. Think of Brownian motion. Infinitely many Brownian particles satisfy the diffusion equation. So Z would be a density, and here's the diffusion equation written down. And part of the message is, I don't want to learn the diffusion equation. It's important that I learn an equivalent representation of the diffusion equation. And the equivalent representation is the following. It is minus divergence of rho times the gradient. This quantity in pink is a differential operator, and that is the operator k I want to learn. And then for Brownian particles, the entropy is trivial, has been known for 150 years. It's the Boltzmann entropy. So to convince you that what I'm doing is right, let's take the entropy, let's differentiate it. I take the variation derivative, I get minus logarithm minus 1. The operator is now taking the spatial gradient. The spatial gradient of the logarithm gives 1 over rho times by the chain rule gradient of rho. If I plug this into this expression minus divergence of rho, this rho and this rho cancels, the minus signs cancels, and I get divergence of rho, which is Laplacian. So really this is an equivalent representation of the diffusion equation. And I want to learn such a similar structure for more complicated equations. And I claim that this structure is better than the nice Laplacian, which looks weird since the Laplacian is the nicest operator we can think of, it's linear, it's everything. What's the benefit of this complicated nonlinear structure? I claim the benefit of this structure is that it contains additional physical information, which I don't see if I look at the Laplacian. And before I come to the algorithmic idea, I really want to make this point. I've written the equation I want to learn, the evolution of the trajectories I want to learn in two different ways. And that is, in my view, an important challenge in machine learning. It's this question of non-uniqueness. Do I want to learn the evolution here, in this case, as diffusion equation, where the operator is the Laplacian, or do I want to learn the structure I claim is, in a sense, better, namely this operator K acting on the entropy? And what I want to emphasize is that I'm particularly interested in learning the structure, and I claim that the structure is a good one. One of the reasons is the structure here immediately tells me physical information. It tells me, one, what the entropy is. Second, it tells me that the entropy behaves in the way I expect it to behave, namely it's a monotone function in time. And yeah, so there is physics behind the representation I want to learn. And we're not the only ones who are doing this. There's a fair amount of related literature. I just put it here on the board. I don't think I have time to go through this in detail. But there's a number of very interesting works. So structurally related is GFIN, which is trying to learn the so-called generic formalism. And in a sense, one could say we try to learn here half of GFIN and give rigorous error estimates. So I've explained what I want to learn, and I said it's important that I put the physics in by learning thermodynamics. Now comes the trick: how do I learn? And the good way to think about it, so it's very nice to be in this session, since this session is about noise and learning dynamics from noise. What I want to implant in your brain as a way to think is that we have these particles which will provide the data we are learning from. This is the PDE we want to derive, the evolution of the PDE we are trying to learn. The player is something in between. So for people with a physics background, you might know this. It's called the equation of fluctuating hydrodynamics. It's called Dean-Kawasaki equation. And that is what singles out this thermodynamic information. What you can think about this is, you have the particles. If in mathematical theory I take the particle number to infinity, I get a nice PDE. And now let us think about what happens if I don't send the particle number to infinity. In experiments, all the data is finite anyway. What happens is, for finitely many particles, you will see oscillation, you will see fluctuations. And those fluctuations are what I'm going to use. They encode the information about the PDE. And we are not the first one to see this. I learned, actually here in Asia, a nice quote: the physics lies in the fluctuations. Yeah? And this is kind of what we are trying, is to give a mathematical, rigorous framework of this quotation. So this is the one technical bit I have to tell you. Really, this is a core idea. And there are formulas, but I hope that we really get the idea here. What I want is, I'm now thinking about what do finitely many particles do. And for infinitely many particles, I now try to write down in a more complicated way what I want to do is, I want to learn the PDE, which has the entropy. And since we don't want to talk about linear diffusion, we want to make it interesting. For nonlinear diffusion, there's a transport coefficient, which I will call M. So this is kind of the structure where we have tested the method with, and where for some cases we have error estimates. So this is the operator I want to learn. So that means I have to learn the entropy, and I have to learn this divergence of m of gradient. That's the aim. And the trick is, I don't try to learn this directly. Instead, I ask, what happens if I take finitely many particles? Like here, I put a Dirac at every particle, and then I look at the so-called empirical measure. I just follow the collective evolution of n particles. And then there is a theorem, but I'm here just giving it an informal way. The information is the evolution of these finitely many particles is what I'm trying to learn, a deterministic equation, plus a stochastic correction, which is of this ugly looking structure. There's a space-time white noise involved. There's a square root, which is, if you think about ODE theory, is bad. Yeah, it's a non-Lipschitz term. It can destroy uniqueness. And even more, there's a divergence in front. What you see is this noise becomes small if the number of particles goes to infinity, as it should. And in an abstract way, what I'm trying to learn is the deterministic PDE. This is what I'm really interested in. And the finitely many particles have the stochastic perturbation on top. And I claim that one, if I deal with real data, I always have this. Yeah, I always have finite data. The second claim I make is this stochastic equation is in fact better for learning than the deterministic one. And that looks surprising, since this equation is far more complicated than what I really want to learn. But why is the stochastic equation easier? And now to explain this, I will be very brutal. This is a very complicated SPDE. Let us compare to an ODE. Suppose I want to learn the ODE x dot equals f of x. Okay, quite simple. And what I have is a stochastic perturbation. So I don't have x dot equals f of x. I have x dot equals f of x plus noise with a prefactor, a volatility square of sigma. What's the benefit? The noise I can learn easily for an ODE by looking at the so-called quadratic variation. Namely, I simulate this ODE, I look at a trajectory, I evaluate it at consecutive times, t0 and t0 plus h. I subtract, I square, take the expectation and divide by h. This is the so-called quadratic variation. This gives me the volatility. The take-home message for this method is exactly the same works for PDEs. Now, this is what we're going to use. And why is this better? What's the benefit of the noise? Remember, I want to learn the structure. I want to learn the entropy S, and I want to learn the evolution operator K. There's two players. This deterministic part contains both players. It has the operator here and the entropy. So it's very hard in a machine learning approach to say this part is part of the entropy and that part is part of the operator. The noise is easier, since the noise, I had it on the previous slide, well, you see in the noise there's no entropy. The noise only depends on the differential operator. So the benefit is we split the problem in two halves. We first learn the evolution operator from the noise, and then we can learn the entropy, and in this way we get a unique representation. And that's important. You will show later on that if I don't do it this way, I get wrong answers. So I'm going to show on 2 or 3 slides how it works. If it's more technical than you like, essence is I do for PDEs exactly what is very well known for ODEs. Namely, okay, well, let me, so what do? I want to look at the fluctuation of the particles. So I look at finitely many particles, I subtract the expectation, then I scale the object such I see the fluctuations. And that's the correct scaling. And then there's a formal way to say what comes out is a so-called Ornstein-Uhlenbeck process. It's an SPD description. Evolution in time is given by something deterministic, and then here an object which has the noise in it, and this mobility I'm trying to learn first. And so for the moment, in the first step, I say, okay, I assume that my operator has the form divergence of an unknown m applied to the gradient. And I just try to learn this transport coefficient m, and what physicists would call, would use mean displacement methods for. And there's a formula which we initially derived formally, which is exactly the analogous formulation of what we had before. I look at trajectories at consecutive time steps, take the difference, square, take the expectation, divide by h, and send the time step to 0. And that works. So just to show you some example, if I try to learn m, and for the time being, I say I know what the entropy is, and I know that my operator has a structure minus divergent of unknown m times the gradient. If we apply that to some particle methods, so we use various test cases where we can compute analytic solutions and can compute the mobility m with the way I've shown before, and the essence is the only relevant information is there's a very good agreement. So up to the naked eye, you get exactly the right answer. And that's something we did a while ago. It's not what I promised. It's only computing this m. It's not computing s, and it's not computing the overall operator. But one aspect is, if I do the same thing, only I'm a little bit more sophisticated to say, now let's learn k, which is this minus diversion of m of gradient. I use the same ideas. It's a bit more complicated. It's not a number I'm trying to learn, not a function. It's an operator. But method is the same, works. So what I'm now really trying to do is I want to learn the operator k. From particle data, I assume that I know the entropy or its derivative, which I call here f, and now I want to learn the full differential operator. And one can show that the same idea works as I've indicated for the mobility. In physical language, what we are kind of deriving here is an infinite dimensional fluctuation dissipation statement. I'm saying the dissipation k is related to the fluctuations, and the fluctuations are the square root of k. Now that's what physicists would call a fluctuation dissipation statement. So in essence, a fluctuation dissipation statement allows us to compute this operator k. And yeah, I'm skipping it's just an implementation. And okay, now thank you. So they see a movie here. But maybe not. Okay, if it's not coming, so I think you need to give right to show the movie. If not, we just move on. So what we were doing is, it's a pity, it's a nice movie. We were looking at particle data. We computed the evolution of the density until it reaches equilibrium. And for the full long time evolution, there was complete agreement with the particle data and the PDE. So what happens is you have an initial data which was a cosine function, and then it's diffusive, it becomes, it converges to equilibrium, and you see you don't see, but you would have seen the full evolution to equilibrium, meaning the method is in fact capable of making long-term predictions. So that means I'm relatively at the end of my talk. I'm done with half of what I want to do. Namely, I've learned the evolution operator K. And the important point really was I learned K first from the fluctuations, since the fluctuations only contain the information about the dissipation operator, they don't contain information about the entropy. Now I can come back to the deterministic part and say, okay, the deterministic part is the operator K, which I've just learned, acting on the entropy ds. K I know, so now in a second step, I can learn the entropy. And for this, we just do a neural network approach. And in this way, we can learn the entropy, and therefore we have learned the full evolution equation. And this does work, but I do again want to emphasize this non-uniqueness issue is important to me. I can write the evolution in infinitely many different ways. I can say it is this evolution with K, it's an L2 gradient flow of the Dirichlet integral, and so on. There are infinitely many ways. If I want to learn the evolution reliably, I don't know any other way of doing it. Since the fluctuations tell us K uniquely from microscopic data, and then we learn S. Here we were using this method for an equation where we don't know the governing PDE, so-called Arrhenius diffusion. The particle model you can write easily down. The governing PDE is unknown. And what we compared is our method and Monte Carlo simulation, so starting from an initial profile, and then here you see the evolution over time, it becomes smoother. And what is good, and so there's third data, it's not easy to see, which is if we only use physical informed neural networks without the particle information, the evolution is pretty good. So the physical informed neural networks, which doesn't use particle data, gets the evolution almost as good as we do, and significantly cheaper. But if we then ask a physics informed neural network without the statistical mechanics information, what is the structure, what is the operator K, we get a completely wrong answer. So this is kind of indicated here. This is a visualization of what is learned as the operator. The correct one is this one. The physics-informed neural network gives you something completely different. And this is the non-uniqueness issue. Yeah? The physical-informed neural network, different from ours, the one which doesn't use statistical mechanics, gives us a sensible evolution. It does give a gradient flow structure, but it's one we have never seen. I don't know what this operator should be. So you learn a structure, but the structure has no meaning I can attach to it. And that's why the thermodynamics is important to me. We learn the operator which is given by thermodynamics. But again, I want to emphasize really the evolution you can get almost as good with cheaper methods. What I really emphasize is the structure. I want to understand the structure of the evolution, and for this, the fluctuations are crucial. And I think, yeah, that's probably the penultimate slide. Yeah, okay. In fact, this does matter. It's again, it's Arrhenius diffusion, and there's a prediction if the interaction is long range, and the upshot is the entropy one gets is wrong if one applies here a wrong limit passage, or if one just uses standard physical informed neural networks. While the fluctuation and the Monte Carlo simulation agree very well. And that's something, here's a reference where we have used this for this example of Arrhenius diffusion. And the last statement is uncertainty quantification. So it was a method, and I've just developed it, and I've computed brute force. Okay. The question is, can we say something about uncertainty quantification? And there's one approach which I haven't approached done, but Celia Reiner with one of her students has used this, what they call statistical physics-informed epistemic diffusion models to reduce the uncertainty, uncertainty in the computational method. We have a different approach. We are mathematicians. What we have developed here in a reference early this year is a rigorous error estimate. Namely, what are the players in my method? I simulate particles. So I have a particle number n, and which is this n, and I simulate over time step t, time step h. And then this is the encoding of, this is what we compute, and this is the mobility we want to learn. This is only to get an error for the mobility, not for the entropy, not for the full operator, only for m of rho, which for this particular process is rho times 1 minus rho, where we can prove things. And there's a rigorous error estimates in terms of the step size and the number of particles we have. So we can, for this process, compute the mobility up to arbitrary accuracy, and that's a mathematically rigorous statement. Okay, that's, I think, all I wanted to say. Thank you for your attention.
Okay, sorry, we don't have time for questioning. So we will go to the next talk. Thank you. Okay, our next talk is Jian Hu from Nanyang Technological University. I don't know, I'm wondering, usually we call the technical university, why here is the technological university? Is there any difference? Usually we call the technical university. Right, because your one is technical university. Okay, the same meaning. Dr. Hu is currently a research fellow at the Nanyang Technological University. He received his PhD from Huazhong University of Science and Technology. His research interests include machine learning theory and mathematical physics. So let's welcome Dr. Hu.
Thanks for the introduction, and thanks for the organization by Kopernik Institute. I'm very happy to have this opportunity to present my recent work here. So today I will introduce a kernel method for the learning from structured data. So, so this work is joined with Professor Juan Pablo Ortega. And I will introduce this presentation in these following 5 sections with a focus on the structure preserving, learning, and the convergence guarantee. So first, the objective. So why structure matters in learning? So actually, since the times of Kopernik and the later Galileo and Newton, one of the central ideas of modern science is that the governing principles can be expressed by mathematical structures. These structures may take the form of geometric constraints or conservation laws or differential equations. So the data in science are not arbitrary, actually. So they are generated by the underlying mathematical structures. So in the machine learning problem, if we ignore the structure, we may lose the stability of reliable prediction. So here is the motivating example, the Hamiltonian system, which can be governed by this equation. We know that the trajectories of this system lies in the level set of the Hamiltonian function. and that means the energy is conserved along the trajectories of this system. So in the machine learning method, if we ignore the Hamiltonian structure, we may lose the long-term stability and get wrong dynamics. So actually, in my previous work working on this direction, we make some efforts for the learning of Hamiltonian systems while preserving their Hamiltonian structures on the Euclidean space, and later we extended the method to the general Poisson manifold in the manifold setting, and then in the infinite dimensional density manifold. Yeah. So here, the objective here is going beyond Hamiltonian structures. So we know the Hamiltonian structure involves a vector bundle composed with a gradient operator. But here I want to look at the general linear differential operator. So in our observation model, we suppose that we observe the samples xn and yn. So xn are IID drawn from a probability measure in the domain. And yn values the function h at these samples, while this h has a hidden differential structure, so which is given by the differential operator PS. Yes. So the goal here is to recover the mapping from the input function h to the output solution u, while respecting this differential structures. So this is similar to a critical application of this method is the operator learning of partial differential equations. I will show some numerical experiments later. And there are two major paradigms for handling this problem. The first one is the operator learning perspective that estimates the solution mapping from the input space to the output space. However, this method requires amounts of training data, and their performance are highly sensitive to the choice of sampling strategy. The second method adopts a more direct way. The idea is to import the input. The idea is to put the differential structure into the learning algorithm, and then you train the loss function. So typical examples are the neural networks. However, I emphasize, as I mentioned, the goal is to learn the mapping. So here, if you want to, if you use the neural network, any change of the input function will require expensive retraining. So actually, this is not good. A good way to do this. So kernel method provides a data effective and easier to train choice. Yeah. But currently, a common strategy for kernel method handling on this structured data is that they put the differential structure. They use the differential structure to define the feature map, and then construct a reproducing kernel Hilbert space. And so in this way, they can transform the original minimization problem in the Sobolev space to a traditional kernel ridge regression problem. And then you can do it. However, the problem here is that the constructed kernel is not explicit. So sometimes it will satisfy some very complicated partial differential equations. So it's not easy to compute in practice. And another thing is that there is no guarantee for that the constructed kernel is universal. So here I mean the kernel is universal. It means that it's associated reproducing kernel heap space is dense in the continuous function space over any compact set under uniform norm. So in this talk, I will, our approach is also kernel method, but we call it structure preserving kernel learning. So here, the strategy is that it's very straightforward. We just put the differential structure into the learning algorithm, and we seek the optimal functions within the reproducing kernel heap. So here, the HK is the space we call it reproducing kernel heap space. It's a And in this way, we can choose any kernel function. Yes. So for example, we can choose universal kernels, but there are new problems if you do it in this way, because here we take the high-order derivatives over the functions within the RHS. So it means that you have to guarantee this is well-defined. Then you have to solve the well-posed of this minimization problem. The second is that it seems that here we still learn one singular function, yes. Yeah, but remember our goal is to learn the solution mapping. So the advantage of kernel method is that we can show that this minimization problem will admit a unique solution which has a closed form. Then you will see that this closed form is independent on the input function. So it means that the learning algorithm doesn't depend on the retraining. And finally, we will so in this way we can shift the problem solver to the solution operator. Yeah, and then we can analyze the error bound. Okay, this is the idea. So first, how to guarantee the well-posedness of this minimization problem? So here I present a so-called differential reproducing property. But here the property is on the general Riemann manifold. So of course you can apply it to Euclidean space. So it shows that if the kernel is regular enough, for example, is in CB2S plus 1, then you can embed the corresponding reproducing kernel heap set, HK, to a regular space. So it means that you can take high-order derivatives for the functions in this architecture. More importantly, a differential reproducing property hold. It means that if you take the derivatives over the functions within the RHS, then it can be computed by the RHS dual by the derivative of the kernel sections and the function itself. So in this way, we can give a computational implement for the optimization problem compared with the traditional regularization method. Yeah. Okay, and then this property not only guarantees well-posedness of the minimization problem, but also provides an operator framework for the learning, for the kernel learning. So here is the operator framework. So we can show that if the kernel is regular enough, we can use the differential reproducing property to prove that the differential operator is bounding linear from the RHS to a L2 space. Yeah. And then you can compute the corresponding dual operator, and here the operator BS. So this, as I mentioned before, this is a computational implement for the kernel method. You can directly compute the estimator. Yeah. And then you can get the operator representation of the minimization problem, which is given by equation 2.6. But here, the capital N means that it is the empirical version of the operators I just introduced. Yeah. In practice, equation 2.6 is not convenient to compute, yeah, because they are operators. So in practice, we actually use the kernel representation. So we further derive the kernel representation of the minimizers. So we show that the unique minimizer admits this closed form, where the coefficient C hat is given by this formula. Yeah. So here the PS10 means that you take the action of PS acting on the kernel, the first variable of the kernel. So PS11 means that you act the kernel in both in the entire variables, acting with the differential operator PS. Yes. And a very interesting property is that if the kernel, the regularity of the kernel can guarantee the positive semi-definiteness of the matrix here defined here. So we call it generalized grammar matrix. Yeah. So it means that if you have the regularity of the kernel, you have the positive semi-definiteness of this matrix. Then the coefficient C hat is well defined. Yes. Okay. So remember that we want to learn the operator, yes, from the input space to the output solution. Here is an estimator, yes, it's just one single set solution. So how to shift the solver to solution operator? So here the idea is that because we have the specific form of the minimizer, yes, we have a closed form. So we can pre-compute the kernel base just using these samples and the kernel. So it is independent on the input functions. And then for any input functions, you can compute the solution by just computing this Euclidean dual. So it means that so this shows a very simple but effective way to compute the estimator for any input functions. Yeah. So it means that this method you don't need any training actually, and but you achieve the same performance like operator learning. Yeah. Okay. Now for the convergence. So here, as I discussed in the previous operator framework, we can define the solution operator, yeah, empiric solution operator, using the formula 3.1. Yeah. And actually, we will see that this estimator will converge to the true solution estimator, yeah, as we want. The idea is to decompose the total reconstruction error by 2 parts, and you can estimate each part. Yeah. So here is the result. So we can show that as the sample size tends to infinity, with a very high probability, the uniform norm of the total error under over any source-induced space will converge to 0. And actually, we have the specific convergence rate, which is the minimum of these 2 terms in the formula. So here I will omit the proof, the details of the proof. You will see that we decompose the total error into 2 terms for the estimation error and the approximation error. The approximation error is always has a standard way to guarantee that using the source space introduced here. Yes, and the estimation error we can get the estimation error using some probability tools. For example, the concentration argument of random variables in the of the operator, self-adjoint operators, and also the Bernstein inequality and so on. Yes. Okay. Now I show some examples. So actually, in our setting, we use the differential operator. Actually, you can consider the time as one part of the one dimension, the time as one dimension. So here, so we test many examples, but here I give an example. I show the heat equation. So it is time. It's a evolution equation. So, but you can still consider time as a one dimension. Yes. And we test our algorithm using this family, consisting of maybe 100 functions. So the idea of testing is that we use these functions to serve as a solution of the heat equation, and then we compute the corresponding input function f, and then use our estimator to acting on this family, the input family, to get the estimated solutions. Then we compute the relative L2 error and the relative L infinity error. So the last slide is the performance. So we see that it only costs a few seconds. Then you can get very high accuracy while achieving the operator learning framework. Yeah, you can learn the solution for any given input function f. So here we learn the solution mapping from the input function f to the solution u. Yeah. And if you look one singular solution, for example, you take the first function in the testing, then you will see the ground and the prediction aligns very well with the ground truth. So actually, if you look at the evolution of the heat solution, it will diverge, maybe diverge to the uniform norm, but it diverges a bit. And our estimator also has the same property. Yeah. And the error, absolute error, is very low. Yeah. Okay, and we also make a comparison with the operator learning. So we test the Helmholtz equation, but with both low frequency and high frequency. Yeah. In the test family, we choose two families. Each family consists of 100 functions. Yeah, 100 functions. We test the smooth functions and also high frequency functions. And these functions are served as the solution of the equation, and you can compute the corresponding f. Yes. So here is the performance comparison. Yeah. So we see that for lower frequency, both methods worked well, but our method still works better, and the accuracy is better. Yeah, at least one more order. Yeah, and the cost is much high. Of the green operator learning is, of course, is much bigger than our method, because they need a very expensive training, of course. And if we look at the high frequency case, our method is still stable. But the green operator learning is not good now. Even the training error is very low, but the performance for the testing is not good. And you can see for the one singular functions, one singular solution. For example, for the low frequency, it seems that both methods worked well, but our method is still better. And you will see that the green operator method has some small errors near the boundary. So it makes sense because the boundary condition is not a hard constraint in the operator learning. So it may have some small error near the boundary. But if you look at the high frequency solution, the green operator we have failed. We have even the training error is still very low, but the testing is not good. But for our method is very stable. Yeah, you can actually fully get the very good solution for the very high frequency function. Yeah. Okay, so I will end this presentation with this summary and outlook. So in this presentation, I present a structure of well-kernel method for learning of solution operator from structured data. So this structured data, we can use it for any differential operator. So it means that you can do it for PD learning and so on. Yeah. Also for the Hamiltonian system and also for many general systems. Because here we deal with the general differential operator. And we can achieve some good properties, such as the faster computation, and high accuracies, and reliable extrapolation. And we can give some theoretical guarantees. So maybe in the future, there are some interesting topics in this direction. For example, the extension to nonlinear PDs or applications to high dimension systems. Okay, thank you very much.
Okay, we have 5 minutes for discussions. So any questions?
Maybe I didn't notice this part. Do you have any bounds or estimates on the error in the context of like the differential operator is
Oh, you mean the specific bound, yes?
Yeah, any dependence on the order of the operator.
Yes, yes. If you look at the boundaries of the operator PS, there is a number here, yes. So here, so CDS plus one, CD plus D plus S. D is the binomial number, and C is a constant for the uniform boundary of the coefficients phi. Okay, the C is the boundary, and the kappa is kappa is actually is related to the kernel. It is the CB2S norm of the kernel. Yes.
Actually, my question, if you go one slide back, if that's, I think you denoted it, maybe buried it. You had an alpha. You had a partial derivative with respect to the...
Oh, you mean the operator, yes?
Yeah, so do you have a dependence on alpha in this representation, or maybe you call it differently? Is there a dependence?
You mean for different S, yes?
For different alpha. Yes, okay.
Yes, different S.
Okay,
yes,
okay,
yes, yes. So the relation to S is I think is in the binomial number.
Okay.
Yes. It's CDS plus one. CD plus SD. Yes. The number is. Yeah.
Okay. Thanks.
Yes. Thanks for the question. Yeah.
Any more questions? Okay, if no questions, thank the speaker again.
Thanks. Yeah, thank you.
Okay, now we have a coffee break, and because we have done the group photo already, so we will have 40 minutes coffee break.
does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the three laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied back propagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1-kilometer-long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, From sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated, and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the three laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Amthel invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. Chas Park website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. Chas Park website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices. From sparks of discovery. From inspiration sparked by the clash of ideas. From elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics, respectively. In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy.
This is a gentle reminder that our sessions will resume shortly. Please return to the venue.
Coming. Okay, after a break, the first speaker is Professor Michael Berninsky, right? Berninsky from the Great Bay University. And he's a professor at Great Bay University and previously served as a professor of mathematics at the University of Edinburgh. And he's the director of internationalization for the College of Science and Engineering. His research interests include information theory and information geometry and mathematical foundations of deep learning and the uncertainty of the quantification in dynamical systems. Let's welcome Professor Berninsky.
Yeah, that's what. Okay, thank you very much for the invitation. Given the introduction, I'm relatively new to China. I'm a recent move, so I don't know too many people. I'm always happy to get in touch and get to know people in various parts of China. So let's see how this goes. When I proposed the talk, the title of the talk, I didn't know how much time I had. So it turns out I have less time than I thought. So I decided to squeeze the talk. I will probably run over several slides, and I just focus on one particular aspect of a larger topic that I was going to talk about. But by means of introduction, maybe, since we don't know each other, this is kind of the general area of topics that I've been working on for the number of years. So kind of, I focus sort of the use of information theory and stochastic analysis for, broadly speaking, uncertainty quantification in dynamical systems, Bayesian computations, and more recently machine learning. Sort of another topic is sort of information geometry, again, using that framework to sort of understand foundations of machine learning and various aspects of learning on neural networks, and also sort of stochastic filtering and data simulation in dynamical systems. So I'm listing these things in case someone wants to talk to me about other topics beyond the one that I'm going to talk about today. So as I said, I'm going to sort of squeeze the general topic. Actually, I will talk very little about the geometry, about the information geometry of machine learning, and I decided to focus on one particular class of generative neural networks. I will just very superficially highlight the potential issues that arise when one tries to look at it from the sort of through a geometric perspective. And I will focus on a cautionary tale or kind of a journey of a more mathematically minded person going through computing science literature and discovering relatively shocking statements. So that's kind of, and to my surprise in the end, discovering how a combination of luck can lead to correct results, despite the assumptions and interpretation being correct. So it took me quite a while and a lot of hair pulling before I got sort of the computer science literature. When I got it and when I understood it. So I'll just briefly go. I'll focus on what is called Boltzmann machines. This is a relatively old class of networks. Again, as a more mathematically minded person, I'm at least 10 years behind the current developments. So this is again more of a cautionary tale. In my defense, I mean, Boltzmann machines, old class of networks, but they are still relevant in some aspects of modern machine learning, especially when it comes to neuromorphic computing and spiking neural networks. I mean, the similar techniques, or actually Boltzmann machine sort of surrogates, are used for pre-training those networks. So that's kind of the still, but we'll see how it develops, but many labs are looking at neuromorphic computing. And it turns out that also, sort of because these are so-called energy-based methods, there is a potential use of them in quantum computing as well. I'm not going to talk about these applications. I will purely focus on these as an example of generative neural networks, meaning that these are neural networks that generate probability distributions as you run them. So then I will focus on I'll say something about the training of these neural networks, and then about the specific way of approximate training of these networks, which is referred to as the contrastive divergence. All of this was fathered by, well, the godfather of AI, Jeff Hinton. So he came up with this notion as a potential solution of approximate training of Boltzmann machines, and that's where the main issue lies. And basically what I will be telling you about is that the notion of contrastive divergence is completely superfluous. Right? So a lot of people, there's been a lot of papers on the topic, a lot of people looking at the accuracy, feasibility of contrastive divergence. The claim of this is that actually no one has been using contrastive divergence despite talking about it for a long time. So that's going to be the cautionary tale. And then I will say a few things briefly about the robustness and accuracy of Boltzmann machines in this context. And the relevant thing here will be, or the message will be that luck sometimes helps people with results, especially for Boltzmann machines when people were looking at the accuracy of contrastive divergence as an approximate method for training them. I will argue that people were lucky because this approach was not quite right, and people were lucky because of the specific nature of the spectrum of the cost function, and basically near degenerate Hessian, which seems to be a fairly common feature in various neural networks, and I'll say more things about this in the context of Boltzmann machines. So just let me run quickly through the basic introduction. So maybe don't focus too much on details of these expressions. I will try to highlight the most relevant parts. But first, to focus attention, what I consider, so what are Boltzmann machines? I mean, they are just graph-based networks with binary neurons, sigmoidal neurons. Then there are different classes of Boltzmann machines. So the standard ones are fully connected graphs, where the state of each neuron gets sequentially updated given the state of all the other neurons. This was the original formulation, again proposed by Hinton. Then very quickly people realized that this is a tough thing to do. People came up with the notion of restricted Boltzmann machines, which were sort of just two-layer graphs, which were kind of, you could look at them as bipartite graphs, and then people extended them to a deeper versions, referring to them as deep Boltzmann machines. And they can be used, they generate probability distribution on these nodes. So for example, if we look at digits, I mean, so each of these nodes here would represent the value at a particular pixel in that image. Okay, it could be faces or many other ways. So these, you can think about these circles here as particular pixels of the picture. Okay, and then when this network is trained and runs, well, it will just spit out number of images with probability of each pixel taking a particular value, well, determined by how we train that network. You can also use them as classifiers in various contexts, but that's not the main. I'm just using the Boltzmann machine as an example here. So what are they? Well, you can quite easily, after doing some computations, relatively simple computations, one can figure out that Boltzmann machines have an associated invariant probability distribution, which has the form of a Boltzmann probability distribution. Basically an exponential probability distribution with sort of energy-like cost function. Okay, so it's quadratic in the values of the neurons. That's the method. And of course, as will turn out to be a problem very quickly, I mean, and that's what caused the demise of Boltzmann machines, was that if one wants to use them efficiently, well, there is a standard problem that also shows up in various sampling techniques in MC, and so on, is that you have to be able to efficiently estimate the normalization constant. That's a standard problem not just in Boltzmann machines, but in many aspects of sampling and Markov chain Monte Carlo and so on. So then there is different versions of it, also in the exponential form to restricted Boltzmann machines. Again, the same form, except that this energy function will be different here. There's no quadratic dependence in these visible neurons. There's only interaction between these hidden and visible neurons. That's just background information that we will not rely on the specific formulas for the purpose of this talk. So I'm just wanted to highlight that there are different architectures of Boltzmann machines and their various versions. In all cases, the general form of the invariant probability distribution that network can represent will have that exponential form. Okay. So that's going to be one of the few slides that I will devote to I'll just hint that there is a way, that's what I was going to talk about originally, there's a way of looking at the robustness and accuracy of various types of neural networks, in particular generative neural networks that generate probability distributions. There is a way of looking at them in a sort of through a prism of a probabilistic and information geometric approach. So to each network, like for example this one here, well, if we imagine that, you know, if I fix the architecture, what I mean, I'll fix the number of layers and the number of neurons, I'll have a number of free parameters represented by the weights and biases. Okay? I can consider all these parameters, weights and biases as a coordinate on a particular Riemannian manifold of probability distributions. Okay? Where all these weights will constitute a global, in this case, a global coordinate system, on these manifolds. And then there is a whole relatively complex framework that I like quite a lot that one can use in order to analyze what happens with different families of neural networks when you try to make them approximate a particular data set, and when you try to make them learn a particular data set, and then try to figure out what architecture is better for carrying out a particular task. Because then one has to play with offsetting the approximation accuracy with the complexity of the network and perhaps with the non-uniqueness of the networks that you will learn from this. Okay, so there's the issue of robustness and so on. And turns out that there is a whole nice framework that can be used for this purpose. I'm just highlighting, this is kind of just all schematic. But let's say in this case, it's just, this would be my training data set, or the sort of the data, the probability distribution associated with the empirical data that I'm trying to learn, and all the models that I have are on this black curve here, and I want to find the one, a network that will represent in the best possible way the probability distribution associated with the data. Okay, and of course now if you start looking at this in a geometric context, it turns out that the problem can be much more complicated. I can find non-unique solutions and so on, and there is this whole set of analysis one can use for this. But I will stop. I will not go into too many details when it comes to the information geometry. I will kind of, again, go back to Boltzmann machines and just highlight some main steps that will slightly, well, maybe involve information geometry, but not much. So where does, information theory and information geometry come to place? I just said I have now a neural network that generates a probability distribution. The probability distributions will be parameterized by the set of all the weights in that graph. Okay, so I'll have a whole family. And the geometry of that family is something I'm not going to get into details. But the first question will be, if I want to train that network, I have to choose the cost function. Well, it turns out that at least in the context of networks that spit out probability distributions, I have a relatively easy job because I know what I want to find. I want to find a network that generates probability distribution that minimizes the loss of information relative to the probability distribution generated by the data. And for that, I am well grounded in information theory. I know what to use. Okay, there are some other complications, but we will not get into this. It turns out that in that context, I know what my cost function would be, and that's the Kullback-Leibler divergence. Because the Kullback-Leibler divergence has a very well-defined meaning in information theory, and I know that if I consider, so if this P0 is my empirical data, and I'm now trying to find a probability distribution that minimizes the KL divergence, okay, I will find this probability distribution will minimize the loss of information relative to P0. And for discrete set of neurons, I mean, there's a particular formula for this, doesn't matter. The main point is that in this situation, I know that everything is differentiable with W, because I know what is the structure of my underlying networks. So then this problem, minimization of KL divergence, instead I can start looking for the zeros of the gradient. Okay, that's the standard. And of course, that's the theoretical statement. If I want to look at this in the sort of practical sense, well, I have to just do an iterative procedure. I have to just look for that, just do a standard gradient descent in this context, based on a formula again that I have for the gradient. That formula will be relevant in a second. That's why don't pay attention to this, to the exact form of these. These are just second order polynomials. The main point will be that it's a difference of mixed moments. One is with respect to the invariant distribution of the Boltzmann machine, and then there's a distribution related to the data. Okay, so that's the exact formula for the gradient that I will aim to find the zeros of. Yeah. Okay, so what the general setting is quite nice and simple, of course. I just have to find the zeros. I mean, I have to find the minimizer of the KL divergence. I could look for the zeros of that gradient. Of course, in practice, that's complicated for many reasons. I could, okay, if I use the gradient descent, fine. But the point is that if I use gradient descent at each time for different, when I update my weights, I have to compute that invariant probability distribution. If the invariant probability distribution is defined on a high dimensional state space, I will spend forever computing the normalization constant at each time. Okay, and that was the main problem that prevented people from using the theoretically justified approach. So, well, I skip this. Maybe it's just kind of interpretation of what training does. That maybe not. I would run out of time if I go to this. So there came, well, the original idea was due to Hinton, and the secondary was also due to Hinton, and it came as a potential solution to that need for computing the normalization constants at each time of iterating the gradient descent. Because that was complicated. In order to approximate the invariant distribution, one had to run a particular sort of Gibbs update Markov chain. That took a lot of time. So the solution was based on justifications that I'm not going to go into because I disagree with them. The cost function was changed to something that was referred to as the contrastive divergence. Okay, so it was a difference of two KL divergences, one that had the data distribution, another one had a kth step of this Gibbs update Markov chain. And that was supposedly help with the computations. Well, if I compute now the gradient of this form here, I will have the following formula. That's what the people did at the I'm turning things around because it actually took me quite a while to present it in my own language, as the original literature was quite all over the place. The problem is that, of course, if I compute this, I have still a term that involves the invariant probability distribution. So what was the practitioner's approach to this? Well, okay, so let's get rid of that last term. And let's just keep this one. This one is nice because, again, it has the difference of the two moments. And the difference is now that I'm taking the expectation with respect to the kth iteration of the Markov chain. And often that k was taken to be equal to 1. So a much simpler numerical procedure. Right? And then a lot of effort was spent into sort of trying to figure out how good is this contrastive divergence at approximating the zeros of the original. Long story short, okay, so that's what I just said. People first introduced the contrastive divergence, they computed the gradient, and then said, well, there are still terms we don't like, so we're going to get rid of them. And then there was a lot of literature showing, well, these terms are actually small. That was also not exactly true, only in certain circumstances. And then people were left with this particular approximate gradient. Well, the point is that, surprisingly, no one realized that the following situation is that people basically made a circle. The idea is that if I look at the original formulation, when I try to minimize the KL divergence, I compute the gradient of the KL divergence, which I rewrite here, where the expectation is with respect to the invariant distribution. Now, if I were to numerically approximate it, in any case, well, these expectations with respect to the invariant distribution, if I were to try to approximate it using Markov chain Monte Carlo, well, I would put the kth iterate here and try to have this k as large as possible in order to approximate that. Well, if you look now what happens with the approximate, this I call it sort of the CDK training with the tilde, that's the one with contrastive divergence. What you're left with after neglecting that final term is a formula which looks exactly like approximate training based on the KL divergence. Okay. The point is that after many papers and many discussions of this, the claim is that the whole idea, people don't use they did not use contrastive divergence in computations. One could argue that everyone was just using a numerical approximation of the gradient of KL divergence. And you will find tons of papers on the accuracy and interpretation of contrastive divergence. No one is using it. No one is using the gradient of a contrastive divergence, and the notion of contrastive divergence does not enter in the computations at all. It was a long journey for me actually to realize that was the case. I will skip this here, and I will just mention a few things related to the accuracy of the approximate training of those networks. So now I'm going to bundle together what I refer to as so the original training. So oops, that's going to be the one that is with a sort of the minimizer of KL divergence, and then the approximate one, which has the CDK subscript. That's the one that is trained by finding zeros of that approximate gradient with the expectation with respect to PK rather than with respect to P invariant. And then if I want to now look at the accuracy of that training, so I'm no longer considering the contrastive difference between contrastive divergence and approximate KL, because I claim that structurally they are the same. So I'm just going to look at the accuracy of a method that uses this approximation to the gradient. If I were to do this now, well, as an evaluation, I'm going to look at the error which is defined in the following way. So I call it relative error. It's normalized with respect to the value of KL at the original minimum. It's just the difference of the loss of information in the invariant probability distribution with the contrastive divergence weights versus the theoretically justified one. Then there is another section where I can look at this structure from the point of view of information geometry and from the point of view of the geometry of the manifolds of these networks. More can be done, but as I keep repeating, I'm not going to focus on this. I just want to get to the point and highlight why these methods that claimed to be based on contrastive divergence, people were analyzing, well, how good does the contrastive divergence do? What is the bias in the weights and so on? And look, it comes out quite okay. The point is that, again, the reason for this was not that there was little bias between these weights and these weights. The point was that it turns out that the landscape of the cost function is very flat. And I have some more rigorous results pertaining to this. So now if we consider, this is just the first order approximation to the problem. So that error can be represented in the following way. So this delta here represents the bias, and this term here, which is sort of the sensitivity matrix, it involves the Hessian of the cost function. So now we can see, if we look at the relative error, well, it depends on the combination between the bias in the approximate weights, and also it depends, this part tells me something about the local geometry of the cost function. So there are two ways. Either I can have small bias in the trained weights, right? Or the other option for small error is that when this sensitivity, in particular the Hessian, where it has a lot of near zero eigenvalues. Even if my bias is large, if I am in the region where the loss landscape is very flat, it might turn out that I can use weights that are still very biased, but if the cost function is very flat, I might end up in obtaining good accuracy. Again, looking at the literature, I'm just highlighting that sort of a similar behavior. It turns out that this sort of what people refer to as flatness of the Hessian, near the degenerate spectrum of the Hessian, it shows up throughout literature in various other types of neural networks. I'm going to stick to Boltzmann machines because for that I have rigorous results. What I suspect is that similar results can be extended, at least in part, to other types of networks. Because this feature of the flatness of the loss landscape, at least around the dominant minima, turns out to be fairly ubiquitous in number. So this is a paper, I mean, Jan LeCun is one of the co-authors here. And what this shows here, basically, well, this, I made it too small, but this is kind of a histogram of this represents the spectrum of the Hessian of a particular convolutional neural network, I think. What you can see here is that and there are different sizes of these networks, but there is a bulk of very, nearly zero eigenvalues, and there are a few larger eigenvalues in the Hessian. It turns out to be a fairly typical structure and what this means, well, so if this is the Hessian of my loss landscape, it means that there are a lot of directions locally that are very slowly varying. They correspond to very slow variations in the cost functions. And there's only very few directions where there's a significant change. Well, what that means is that if my minimum is very flat, then it indicates that even if I make a mistake, if I have a bias in the weights I train, the flatter the area around the minimum, the bigger the mistake I can make in weights, I will still be good in terms of accuracy. And in the Boltzmann machines, this then turns out to be what saves it. So it's not contrastive divergence. It's not that contrastive divergence is particularly good at training. It's the fact that Boltzmann machines, that the loss landscape in those functions, in those networks, is such that the dominant minima are very flat. I'll skip over that because I am running out of time. So a few, don't look at details maybe too much. I'll just highlight the main conclusions. We can show rigorously that for either the contrastive divergence method or for this approximate KL, when I use the kth iterate of the Gibbs-Abder-Markov chain, that if I try to figure out what are those trained weights, I can cast this problem as basically with using a perturbation theory. I can turn the problem as finding roots of a polynomial, and then when I look at the approximate method, I can represent it as, so I can look at it as solving a perturbed problem. And then from classical perturbation theory, I can say many things about what might be happening with those roots relative to the true roots that are trained based on KL divergence. And it's not difficult to show that there can be many different situations where there will be spurious solutions, where sort of solutions can show up, the biases can be quite large and so on. So we really cannot rely on the contrastive divergence or the approximate methods to return weights that are guaranteed to have a small bias. That because I can cook up a lot of different examples. So we have to, it turns out that, to repeat, what causes the good performance of contrastive divergence in this context is the flatness of the Hessian. Do I have only like 3 minutes or something? Okay, so I'll rush. Okay, so let me just maybe skip through the point is that if now we can look at the structure of the Hessian in a specific way, and I'll stick to that. So if this is my cost function, I can represent the Hessian. This is exact as a sum of 3 covariance matrices, and that's the crucial part. Because once I'm here in the framework of covariance matrices, I can then show that these covariance matrices will have low rank due to built-in correlations between the components. Okay. This is again an example of a spectrum. You can see those of that. This is for a relatively small Boltzmann machine, but again you can see those of how the bulk of the eigenvalue starts to concentrate around 0. And there have been many alternative explanations of that behavior of the sort of near degenerate spectrum, even for Boltzmann machines. And there were roughly 2 different approaches to this. One was related to random matrix theory, and another one that was related to overparameterization. It turns out that in many cases, including Boltzmann machines, the near degenerate spectrum of Hessian appears for low dimension, even for low dimensional Boltzmann machines, so no overparameterization. And the random matrix theory part assumes independence in the components of the vector that you put in, which can also be easily discarded. So both of them don't really apply. So that's the result from the random matrix theory. So that's something called the Marchenko-Pastor spectrum, which is just an example that it doesn't work. I'll go quickly to the final result and I'll stop here. So what we can show instead is a result where now these lambdas here correspond to the eigenvalues of the Hessian of my cost function. Okay, so this is the Hessian. So this is, if you like, the energy of well, it's just a sum of squares of the eigenvalues. And I can show that now if the n and m is a number of visible and hidden neurons. Okay, the total number of parameters is this capital N, which is nm plus n plus m. That's going to be relevant in a second. But we can come up with the following bound. Okay, so the sum of the first n times m squared eigenvalues is bounded by a particular term that involves only the third order coefficient, third order correlations. We can show that this is small. Okay, so we can show that the sum of the first n times m squared eigenvalues is small. And now if we look at the total number of parameters, which is this one here, if you see, okay, so this is going to be the bulk, especially when n and m are large. This is going to be the bulk of the eigenvalues. So I can show that the bulk of the eigenvalues is bounded by something small, and I have only few left degrees of freedom that have to include sort of the rest of the energy, if you like. So that allows me to deduce, sort of to figure out that there is this the division between the bulk and a lot of small near zero eigenvalues, and then I only have a choice to distribute the remaining energy to a few larger eigenvalues. And I'll stop here. There's just a numerical confirmation of that bound. I'll wait for.
Your time is out.
Yeah, that's why I'm. I'll stay on the conclusion parts. So that's it. I mean, to me, that's a cautionary tale, and actually took a while to reverse engineer the results and realize how much stuff. There are big names associated to these results, to contrasted divergence. And it is a strong claim, but in my opinion, this is all luck.
Okay, thank you. Okay, we will have our last speaker. The last talk, and in Chinese, usually the last one means the most important one. So the talk time is double, so that means most important, right? So because the talk time is double, so my introduction should also be double. Dr. Baibo and received his PhD from Tsinghua University in 2010, and had been a research associate at the Hong Kong University of Science and Technology for 2 years, and from 2012 to 17, he was an assistant professor in the Department of Electronic Engineering, Tsinghua University. Then he joined Huawei and is currently the chief scientist of information theory and the director of theory lab of Huawei. And I just learned he got a new title, the director of Leibniz Research Center in Hong Kong, right?
Yeah, that's the formal name of Hong Kong Research Center, Leibniz Research Center, just like
a new name.
Yeah,
like the Kopernik.
Yes, Kopernik.
So I use the research center, right, or the institute, because I see there is research center. So I copy that to your institute.
Yeah, Kopernik is our research center in Warsaw.
Okay. Yeah. But now the one in Hong Kong is called Leibniz Research Center or Leibniz Institute.
Leibniz Research Center.
Research Center. So
okay, the same.
So I'm right. The same idea. Yes. And let me see. Okay. Dr. Bai served as a committee member for IEEE, ComSoc, and a TBC member for several IEEE conferences. he was a recipient of the Best Paper Award in IEEE ICT 2016. And he's currently an associate editor of IEEE Communications Surveys and Tutorials. So now let's welcome Dr. Bai.
Thank you very much for the introduction from Professor Fan. And thank you very much for inviting me to be here, because as I'm a new title is comes to this April, which makes me very busy. So I nearly have no time on research. So I this talk is actually based on the paper I published on Archive last year from November 2025. Just and I first time to report this research is on the information theory conference of China. So at that time, I explained the title of my report is Forget Bit, because you know the information theories focus only on bit, but I tell them you should forget bit. You should focus on tokens. Then the information theory principles could be very useful for us to understand the fundamental principles of large language models. That's why I use this title. I'm not saying bit is not important, but times change. Okay, so this my research comes from the panel discussion with Professor Edward Ariken in 2023. At that time, the ChatGPT just published, and everybody found that okay, we finally find a way towards AGI. At that time, we organized a panel discussion with Professor Ariken, and at that time, my colleague asked him a question: "Is what's the most important things we are invented during the information age?" So at that time, my thinking is maybe he will say, because he's an information theorist, maybe I think entropy or mutual information or channel capacity or something. But he said the most important thing is bit. Bit is the most important thing in information age. Okay. So that's inspired me to think what's the most important concept in AI age. Okay, this is just my understanding why information bit is so important for the information age. In 1948, Shannon published his famous paper on solving the reliable communication problem from the information theory. In his theory, I think he mainly solved 3 problems. He answered 3 questions. The first one is what does the reliable really means in a digital communication system? We know during this time, many engineers want to build digital communication systems, but they cannot reduce the bit error rate. They tried a lot of different methods, but how can we achieve reliable communication? So in Shannon's answer, he said that the reliable means we tend to the error to 0. We reduce the error to 0 when our code length tends to infinity. It's a asymptotic result, not the finite block length result. And the second question is, what is the mathematical model of a reliable communication system? This is very important because at that time, there is many engineers trying to solve this problem with a deterministic mathematical method. But Shannon said that this is not correct. We need a probabilistic transition probability to describe our channel model. This, I think, is very important contributions of Shannon, because if you use this transition probability, you can see that any communication system, even the one we cannot think of, even the one we are still not invented, can be modeled by this transition probability. Then based on this, we can design the system even without thinking of what it will be like. So I think this is a key for the whole theory. And the third one is he gives some performance measures for reliable communication. The first one is the source coding part. We need to compress the data as small as possible, and then we can use the channels as efficient as possible. So they have the entropy, the limit of the compression. Okay, and he also said that even in a noisy channel, we can achieve a reliable communication only if your transmission rate is smaller than the channel capacity. It's given by the mutual information between X and Y, and we can maximize this mutual information on the transmission probability. So that's introduce a new research area called channel coding, right? We used to code the source symbols that we can combat with the channel noise. So this basically what Shannon does in his theory. We can see that the bit here, the information here is not related to the semantic meaning of the message. It's equivalent to the uncertainty. It's just equivalent to the probability. So that's why in later we'll see that Shannon also realized his research only solves the technical problem, just reliable transmit the information from one place to another. Okay, so in a more general perspective, we can see that the bit not just used in communication system, it also used in computing system, in Turing machines. And this two theory has a very interesting philosophy. In Shannon theory, the delay is not important because in any results in his theory, we always turn the coding length to infinity. So we don't care about complexity. That's why when we are optimizing a communication system, we are always stuck by computational power, even in various in optical communication. The computation power is always not good, not enough. And for Turing's theory, the delay is the most important. When we design an algorithm, we always trying to find the one with the least time complexity, right? So after the last 2 years work on how to accelerate the large language model inference, we are struggled with bandwidth because we don't have the high bandwidth, the most advanced high bandwidth memories. We always move the data from this memory to another one, from memory to our matrix computation unit. We call it a cube, and also we have a vector computation unit. So we always start to move this data from here to another. So we can see that the bandwidth is also the bottleneck for computing, and the computing is always the bottleneck for communication. So, but their interface is bit. So that's why I think Professor Arikin's answer to the information age, the bit is the most important thing to connect the computation and communication. Okay, now we are towards the AI age. We can see that every time when we have a revolutions of the information technology, like the first time there's an interesting book called the Information of Flood, a history, a theory of flood. This book introduced the first 4 information technology revolution, and the totally changed the whole society. But now we are working towards on the AI times. So we can see that from 2023, the large language model develops very, very fast. For the last year, maybe February or just during the Spring Festival in China, the DeepSeek is, I think at that time, is the most popular topics we are discussed, right? But recently, just before the DeepSeek V4 published yesterday, and before that, nobody talked about DeepSeek. Everybody in China talked about the GRM and what's that, and the Minimax, and that kind of model. And in US, most of people discuss about the model from Anthropic with like Opus or Sonnet, and a few people, only less and less people discuss about GPT. So things changed very, very fast. Before we focus on the capability of the large model itself, but now we are considering the performance of a large language model with many, many different tools, which you are into agents, right? So the core is still large language model, but when this agent can solve many problems, you rely on different skills. You can to call many outside functions, outside tools to help you to finish your task. So the things changed very fast. But as the Shannon's paper, we can still ask 3 basic questions for the large language model. The first one is, what does semantic really means in large language model? We can see that the large language model can understand the sentence in his way. Not maybe it's quite different from human beings, but it can understand and it can give you a very good output, right? But what's the semantic? What's the definition of semantic in large language model? And the second thing is, can we give a mathematical model to describe all kinds of large language models? And is there a performance measure for large language model? That's I think the basic question. It's just the same as Shannon answers for the reliable communication. Okay. Okay, this is actually Shannon's paper in 1949. He and Weaver published a paper to discuss the new result for information theory, because at that time when he published his paper, many people argues your definition of information is not real information because you don't consider the meaning in a symbol set. You just consider the uncertainty, the probability of that input set. So they read this paper to say that there were 3 levels of information. The first level is what Shannon mentioned, that is a technical problem, just accurately transmit the symbols from one place to another one. But the second one is not considered in his original theory. How precisely do the transmitted symbols convey the desired meaning? And the third one is how effectively does the received meaning affect conduct in the desired way? We can see that for the level B, it's just for large language model to understand what you are meaning and give you very good, your satisfied feedback. But for the level 3, it's what we are doing for the agent, right? It's just not to give you answer, but it can act. It can execute your it can execute the task you asked. So I think it's a time for us to consider this 2 levels of information theory. As far as I know, In 2011, there is a Center for Science of Information is established in Purdue by NSF. At the last time I visited US, is a workshop in OSU, Ohio University. At that time, they organized a workshop to discuss a deep learning problem, and they invited the director of this center there, and we have a very, very simple discussion on how the information theory to move from level A to level B. But when he knows I come from Huawei, he refused to talk to me. Yeah, that's a true story. And after that, I never go to US. So, but by now, I think the answer is very clear. In AI age, we need to move from bit to token. That's why you can see that recently, especially for the OpenClaw used in many places, everybody talks about how many tokens you use to achieve any result, right? So the token could be the center of AI age, as important as bit in information age. So from my understanding, we trying to answer the three questions. Just I mentioned before, I introduced a few concepts from the information theory. This one is not a new concept. It's we call it directed information. This one is, I think, is key for me, at least for me, to understand the large language model. But why there is directed information? Everybody may know the mutual information, which is a special case of KR divergence. But when 1990, James Massey, he's a student of Shannon, published a paper to say that at that time there is a professor published the first information theory textbook, and he gave a definition of DMC, discrete memoryless channel, is defined as this one, which means that every symbol only affects the symbol right now. The sender, the xi is the transmitted symbol at the time slot I, and the yi is the symbol received by the receiver at time slot I. So this is the simplest channel defined by Ash, but in Massey's paper, he said that this definition is not correct, but every textbook by now still use this definition. So he proposed that there are two definitions for DMC. The first one is that he noticed that this definition has a very important drawbacks, because it cannot include feedback in this channel. And so he suggested what is discrete memory channel is this one. And the channel without feedback, the definition is this one. And when you combine this together, you can get this result. So that's why in Massey's paper, he proposed that if we consider a channel discrete memoryless channel with feedback, you cannot use the mutual information directly to characterize the channel capacity. You cannot do this because you need to consider the feedback in the channel. Then he introduced the new concept called directed information. And this is actually very difficult to calculate in practice. That's why we are using this one. Even by now, we use this definition to derive the capacity for almost all the communication system. We nearly never use this one. Yeah. Okay. But we find that it is very, very important because it has a direct connection with the causalities for a time series. In 1980s, if I remember correctly, the economist Clive Granger, he proposed how to evaluate one time sequence is cause another time sequence, and he proposed the causality. Later they call it a Granger causality. In his definition, means that if there is at time t we have a universe, all the knowledge of this universe, and ut minus is all the knowledge in a modified universe. It excluded the x1 to n, this sequence. In his definition, if this two probability is different, it means that the x1 to n is causes yt. So that's his definition for the causality. Okay, so in many research, it shows that Granger causality is equivalent to the direct information for the Gaussian vector autoregression process. They have very deep connections between the directed information and the Granger causality. Okay, but from the perspective of another professor, is also very famous in machine learning, is Judith Pearl. He has his own definition of causality. He criticized Granger causality is just statistical rather than causal. It's not, from his point, this is not a real causal. It's just statistical with on a time series, on two time series. But I think this is good enough for us to understand the large language model, because this is too, the key idea here is to use the history to predict the future, how much information you use in the information in history to predict the future. That's basically what we are doing in neural networks, in large language model, right? Okay, we can also define some other definition for the backward directed information. This is useful in the following, and we also need to introduce the information density, which is proposed by Dobrush in 1959. By now, this information density is used for the finite block length information theory, because in practice you cannot make the coding length turn to infinity. You need to evaluate, for example, the code length is, especially in the short coding length cases, maybe you only have 100 bits for your code, then what's the achievable rate? The last one is rate distortion function. This one is proposed to evaluate the lossy compression. And you, for example, you compress the source symbol to another one, and when you regenerate the source symbol, what's the distortion between the generated one and the original one with some code constraints. So that's this, we call it a rate distortion function. You can see that in even for any real number, you cannot represent accurately by a finite length of bit, right? So for this kind of compression, you need to define the distortion between the regenerated symbols and the original one with some code constraints, code rate constraints. So this is also very important. So then, from my point of view, the large language model can be expressed by this very simple transition probability. Here we use S1 to N is the prompt, the input sequence, and UN plus 1 to T minus 1 is just the tokens generated by the large language model. If you read the paper, attention is all you need, they will also feed back the output token to the input, right? And based on your prompt and what you have said, and your knowledge, this is a parameter of the model, and then you generate the prediction of the next token. Then you can write the pure probability model of the large language model. Here, F is a module to map the token sequence to a vector representation of this token. Okay, if we see a large language model in this way, we can see that this is just the channel with feedback and state. So I propose to use the just I said, it's directed information to characterize the performance of a large language model from input to output. By now we can forget all the details of this implementation of the large language model. We can see if we know the transition probability, we can derive many things. The first, we can derive the directed rate distortion function from in the pre-training phase. We can see that in the pre-training, we control the KR divergence between labeled data and the generated answers, right? This just the KR divergence in the training phase is equivalent to the cross entropy, and then we can try to minimize the directed information from the input prompt to the generated sequence, such that we only during the training phase we only let the model to remember all the information useful to generated the next token with the distortion constraint. Okay, so if we, this is not very important. If we consider in a post training phase, we can also define in many, like the reinforcement learning with human feedback. In that paper, they propose a DPO method. We can see that they just propose to use a evaluate function, a score function, to give scores for the whole sentence of the output of the large language model. And in this case, we can also use a similar method to minimize the directed information from the input to output. To the constraint is that the answer quality is larger than our threshold, and we can see that by using this as an objective function is equivalent to the DPO. This method in this very famous paper RHF. So we can see that from information theory perspective, we can understand the end-to-end performance from a different angle. And if from this point of view, we can see the training phase for the larger language model is to make this model to approaching the human level granular causality inference for the next token prediction. Okay, because we have many results to show that the grander causality is equivalent to the directed information. Okay, in the inference phase, since it's a little bit different, we need to introduce the information density, because in the training phase, we need to do the average in a large corpus to do the training. But in inference phase, we will see every output of this, of 1 hour question, right? So we need to evaluate the performance for every answer, every trace of this large long-range model's output. So we need to consider a stochastic process which is defined on the generated output sequence. So because of the probabilistic structure, it's very, very complicated for the sequence. So if we use the if we use this information density, we can find that it has very good mathematical properties. The first is this process is Markovian, and also we can show that this process is a sub-martingale. And based on this, we can show some interesting results if this is very direct result based on these theorems. This result shows that when the derivation, when our inference phase stops, which means that the large long-range model, the prediction of the last symbol is stop, just stop symbol. Then when this stops, the information transmitted from source to this output tokens is larger than to the first one. So this is quite obvious, but we can prove it by using this Dup's stopping time theorem. And also, if we use the Friedman inequality, we can also characterize the information, the importance of different tokens generated by this model. Okay, and there is also another very interesting understanding for the prompt engineering. Previously, it's called prompt engineering, and then call it in-context engineering. Now, we also, when we combine the large language model with agent, especially in the coding tasks, we call it harness engineering. That's the same. The basic understanding is that we change the input probability of this prompt sequence, and to make sure that the output quality is as good as enough. This is exactly the same as the idea of Shannon's channel capacity. In that case, we maximize the mutual information to find the optimal input probability. But now here we can see that we want to maximize this directed information with the constraints. The answer is as good as we expected, and we trying to optimize this input probability. So I know that some professors from CUHK, they use some optimization methods. Giving you a model, they're trying to use some optimization methods to find the best prompt. They have some experiment results. Okay, so in the previous part, we see that all the large language model can be understood from a pure probability theory, transition probability model. But I want to say that the most important thing for large language model is we use a vector to represent a token. This is very, very important because when we use before the large language model, we have every different models to to do the NLP tasks, but we cannot extend the to a very complicated tasks. But after we successfully to map a token to a vector, then we can do this, because if we have the vector representation of a token, then we can use the inner product to evaluate the similarity of the semantic. This idea is, as far as I know, it comes from a paper in 1953. There has the original idea is use the vector to represent a token, but the successful comes from Ilias' work. They really train a neural network to represent the token to vector. Their ideal case is the vector of king minus vector of male plus vector of woman, female, equals queen, vector of queen. Yeah, that's their ideal case, but this cannot be cannot be true for all the tokens, but I think it's good enough to use the inner product to represent the semantic relevance. So in this case, if we want to compress semantic vector, it's quite different from the compress of data from the perspective, Shannon's perspective. In that case, we can compress every source symbol to a small, to use as few bits to represent the source symbol. But here, because of the inner product of the two vectors is critical for us to evaluate the semantic relevance. So the thing for compression semantic is the compress the whole space. It's actually to reduce the dimension of the vector. In this case, we need to the change of the inner product as small as possible. That's why we can introduce some JR lemma, which is very useful in machine learning to help us to understand that we can compress the vectors into a small dimension such that the inner product can be controlled. Okay, so from my understanding, because my background is information theory and communication, from my understanding, the vectorization, this part is to change an NLP problem fully based on probability to a signal processing problem. Then we can use many other methods to accelerate the computation. Okay, so so there is I think should be an optimal vectorization. If we remember that the objective of our large language model is to predict the next token, right? This is our task. Then in this case, if we want to map a token into a vector, we need to generate this vector with all the information useful for predict the next token. Okay, there are many methods to generate a vector of a token, but for large language model, I think what we need to do is to generate this token vector representation based on all the previous inputted sequence with the maximized mutual information with the future tokens. right? In this case, this vector has all the information is useful for the next token prediction. This is related to the objective of large language model. Okay, we can see that the solution of this one is just the maximization of our backward directed information. This method is proposed by DeepMind. Several researchers in DeepMind based on a very famous work from Elias. Elias is a very famous information series. He invented the convolution code, and the convolution code is the most important channel coding in 3G area. And this paper in 1955, this paper is just published on the first volume and the first issue of IEEE transaction on information theory. That's part 1, part 2 paper published on the very early, and Google's research based on this, his idea, and invented this, they call it the contrastive predictive coding, which has a deep connection with information theory. And they also, when they want to training this model, they also surveyed all the variational lower bound for the mutual information to make this more tractable in computing. Okay. So following this idea, I think we can write the mathematical formula for the attention module, and just very similar to the energy based model. We can write down this. It can be seen that this is just a auto-regression process from the time series perspective. But the thing is that the matrix is this one. This matrix is learned from practice. This one is just equal to the weight value matrix. And for this part, to model the to model the semantic relevance between one token to another can be decomposed to the query and K matrix. Okay, so from this point of view, we can give some bound for the not just for the transform, for the attention module by using the latent position variable, because you can see this as a probability of choosing the latent variable j, and then we can have some results here. And another, I think the more interesting result is to derive the generalization error of the whole large language model. In this part, what we are, the generalization error is characterized by the cross entropy between the generated tokens and the human output. And if we use this with some tools from they call it Rademacher complexity, we can show that the empirical this is the empirical generalization error. This is generalization error is upper bounded by the empirical generalization error plus the Rademacher complexity and some constant. Okay, this can be obtained from using this complexity and this inequality. So in this way, we can see that we need to control when we do some the quantization of large language model. We find that in practice we need to carefully control the accuracy loss of the logics. But from this result, we can see that this is just the logics which control the upper bound of the generation error. Okay, and the last important thing I found is also from a very pioneer work from statistical physics. At that time in 1988, the Elizabeth Gardner published 3 papers to discuss the capacity of a Hopfield network. They showed that how many patterns can be memorized by a Hopfield. At that time, it's a binary Hopfield network. At that time, the pattern is just a random binary sequence, so this definition has a deep connection with Shannon's capacity. Here, K is the number of patterns, N is the number of neurons, or the length of the pattern is the same. Here, he said that when the N tends to infinity, just as in Shannon theory, we let the coding length tend to infinity, how many patterns can be memorized. And in Shannon's theory, there we add just a log function here. They are almost nearly the same one. So in maybe 2 years ago, Hopfield and his collaborator, it's called Krotov, they introduced a new kind of Hopfield neural network. They use not just on the binary state, it introduced a continuous state neural network with new energy functions. And they show that with this new energy function, with this new continuous state, the memory capacity increases exponentially as the n increase. If we use a log function, it gets the same scale as Shannon's capacity. And in Ramsor's work in 2020, he showed that the continuous state Hopfield network is equivalent to a attention scheme. So they have a clear mathematical result, which means that with not a very large model, we can use attention to memorize nearly all the patterns of the neural network. So that's why shows that why our large language model has a powerful capacities. So we also following this line of research, trying to answer the following questions. Because why we need multiple head attention? Why only one attention is not good enough? There is some conjectures is that the multiple head attention is the principle for the multi-head attention is similar as the replica method in statistical physics. When you study a system, only one sample is not enough. You need to consider the multiple replicas together, and then you can get the good result. So this is just our conjecture. We are still working on these directions. So trying to fully understand the structure of transformer. Okay, the last part is just I think the few directions. As I mentioned that if we from the probability perspective, and if we use the directed information to model the performance of a large language model, we can see that it's human level grander causality to predict the next token. So this is not the real reasoning from logic, right? But how to help our large language model to get the real reasoning capability. To I think a very useful way is to combine with the category theory, and we have some discussions with our Fields Medal list in Paris. Le Hong La Fogue, we have many discussions on this, and recently we found that even Terence Tao also proposed to use the large language model plus Lean to help mathematicians to do math research. I think this part is just as in a very famous book from Daniel Kahneman said that the large language model help us to give some empirical understanding of a system. When we can use large language model generate the code, generate the Lean code, then we can use the Lean compiler to try to compile this code. If it can be compiled without error, we can see that this conjecture is correct. So from this way, we can see that this part is just the empirical part is causality inference, grander causality inference, but this part is logical reasoning, which can help us to verify the generated code is correct enough or not. So even for Huawei, we have another lab fully working on this part, trying to use many compiler tools to verify all the code generated by a large language model to guarantee if it is correct or not. Okay, I think this is the last part of my talk. I think the most important thing from my talk is that we are now in the AI age. We should forget bit. We should fully embrace token, even you are working in information theory. We need token is not just the same as the symbol understand from information theory, because they have semantic meaning is different from symbol in information theory. Okay, that's basically what I'm talking about. Thank you very much.
Okay, any questions?
We use Witten metric or distance in a probability density space, because it's in that way we have a good calculus called autocalculus. But in your token space, why is this distance interesting?
Use Gromov-Wasserstein distance. Yeah, because just as I said before, you in a semantic space, the most important thing is the inner product of two vectors. And then for example, you have two semantic space. How to evaluate a distance for these two semantic space? You need to compare the distance of the distance of two inner product, and then with some probability measure. Yeah, so that's why I think this distance is very important for evaluate the distance of two semantic space, not just for semantic vector.
More questions?
Okay, my question is about the mathematical modeling of the transformer. I take analogy for the score-based generator modeling. So there is a paper by Song Yang's group about we have the stochastic differential equations and the reverse time dynamics, which is basically the very exactly mathematical modeling we are looking for. And most of the algorithm development following these basic ideas. But if we talk about the transformers, recent work tried to use the interactive particle systems to understanding this. But I didn't see quite a unified, this kind of strong mathematical power, modeling for this transformer, playing the same important role for that as the reverse, as the intergenerator modeling. So I would like to hear your comments about mathematical modeling and the computational theory for the transformer structure.
Yeah, I think this part is very important because by now when we trying to improve the structure of transformer, what we can do, we only can do many experiments, right? It's very expensive even for Huawei. So the theoretical understanding of transformer is very important. It helps us to find the most promising way to how to improve it, or it can show us this maybe it's just the optimal one. We cannot change anything, right? Theoretically, what we can do is just to optimize the implementation in our hardware. That's maybe one answer to this question. But if somehow we can find the improvement method, then we can save a lot of money. So that's why I think this theory for transformer is very important. But just as you said, there are only very few results here. But recently, I see many professors from statistical physics have some new results, especially in this year's I think ML or iClear, I don't remember. There is a workshop for, especially for statistical models for transformer. Yeah. But their attention now is on the attention module. But I think the FFN module is also very important, and the residue connection between the FFN and the different layer of FN is also very important. There are some conjectures to see that if there is no this connection, all the results will collapse to one state. And if there is this one, they can have some conjectures to guarantee the result is in different states. Then we can get the good prediction of the token. So there are some preliminary results.
Okay, I think our time is time for dinner, right? Okay, yeah. So let's thank the speaker again. Okay, so the organizers wanted to say something.
Okay. Thank you so much for your very insightful sharing. I think this is a very interesting question from the online guest, which is, since now we may use KV cache and context engineering to realize the memory during inference, can we consider inference as a channel with memory? Yeah. Can we consider inference as a channel with memory?
Not a question. I thought the organizer wanted to say something about a dinner. Not a question again. It's over. Well, question time is over.
I think all the system is a channel with memory, not just for in the inference phase. Of course, it's in inference phase is a channel with memory with feedback. In the training phase, it also is a channel with memory and feedback.
Yeah, the organizers wanted to say something here.
Yeah.
No question more. No question anymore.
Question, please talk with us online.
Yeah.
Okay.
Thanks all the guests' participation. We warmly invite all the guests to join the dinner at Curtis Restaurant. See you there and enjoy your dinner. And at the same time, we can remind all guests that you can scan the QR code to download.